Welcome to this tutorial on wireless for machine learning. It is with great pleasure that we are able to present this tutorial in video on demand format, freely available for anyone interested in the topic. This tutorial has been put together by 4 people: Carlo Fischione, Professor of Internet of Things; Victoria Fudor, Professor of Communication Networks; José Mayrton Barros da Silva Jr., Senior Researcher; and myself, Henrik Helleström, PhD student. All 4 of us are from the Division of Network and Systems Engineering at KTH Royal Institute of Technology, located in Stockholm, Sweden. We will all present different parts of the tutorial, starting out with Carlo Fischione.
Wireless Internet of Things is arguably the current most important technological revolution, and this can be seen or illustrated with this white paper from Ericsson, the major telecommunication company. That paper was released in 2020. In particular, according to this overview paper, wireless Internet of Things can be defined as the world of everything connected, and is creating a tremendous economic growth and opportunities. In particular, there is 4 main areas of Internet of Things called massive IoT, where we will have many devices of reduced computational and communication capabilities, but very many in terms of a number, of the order of several tens of thousands per square kilometer. The other category is broadband Internet of Things, where we will have less devices, but equipped with high data rate communications. Then there will be critical IoT devices, where the communications could be low bandwidth, high bandwidth, but what is important is that messages are received within short deadlines, very short, also milliseconds or less. And then we have the case of industrial automation Internet of Things, which refers to the use of IoT for industrial setups and factory automations. Now, these 4 categories of Internet of Things have several application domains, from smart metering, asset management, drones, augmented and virtual reality, autonomous cars, traffic safety and control, smart grids, and so on. And in each of these cases, we have several distributions, generation of data sources, data that has to be analyzed to understand the system. In the case of, for example, smart grids, the smart meters. In the case of autonomous driving, presence or absence of obstacles, and so forth. And this data analysis sometimes have to be done even with very short deadlines, such as in the case of critical Internet of Things. Now, despite the fact that there are so many different use cases for wireless Internet of Things, as we have seen in the previous white paper, all these use cases actually have very common technological challenges and also research challenges when it comes to machine learning and wireless communications. The first challenge is that the data generation is distributed over many wireless devices. And this is certainly the case in smart cities, smart grids, environmental monitoring, autonomous traffic transportation systems. But the question is that then the data analysis have to be done at places or times which are different from when and where the data has been generated. So this means that in principle, data from so many massive amount of devices has to be transmitted from where it's generated somewhere else. And this is not economically sustainable. Sometimes it's not even technologically possible. Certainly, this is the case of environmental monitoring, where we have many devices in the environment where, due to lack of battery, they cannot transmit continuously data. Otherwise, they would deplete the battery, they would die soon. Again, this is the case in smart cities with autonomous traffic. And in other situations, the amount of data that is generated, such as in autonomous cars, is of such a huge quantity that we are speaking of terabytes, sometimes terabytes per seconds, and the transmission of so much data from so many future autonomous vehicles in a short geographic, in a small geographic area over wireless communications, it's something that it's economically unsustainable due to the cost and spectrum management. So in general, despite the fact that we have so many different use cases, we have as a common set of challenges for machine learning and wireless communications. These challenges can generally be grouped into 6 main points, and they are due to that computational limitations of the distributed devices, communication latency to send data to where it has to be analyzed to build models and to build inference. Bandwidth limitation, because every wireless communication channel has a fundamental bandwidth limitation, and we cannot transmit as much data as we might like. Also considering limitation due to multiple access. Then we have the problem of energy consumption, because transmitting data also means to use batteries of the wireless devices. And then we have problems of privacy and clearly and security. In many cases, such as in autonomous driving, such as in IoT for personal body monitoring, the data belongs to who has generated this data, and we don't want that it be used for purposes that are not wanted by those who have generated this data, who own this data. And then in security aspect, it's particularly evident in the case of wireless Internet of Things for smart city monitoring, smart grids, critical societal infrastructures such as water distribution systems. The now main message that with these prominent challenges that wireless Internet of Things and machine learning are encountering, the main point that we want to put forward is that the state of the art of machine learning and in general artificial intelligence is not yet conceived to tackle these challenges. If we see at an historical evolution of machine learning, as it is represented here in this graph, we have on the x-axis the more or less decades, and on the y-axis the number of connected devices. We can say that in the 1950s we started with a computer, in the 1960s with the internet, and then gradually we evolved with wireless communications, wireless internet, and now the 2020 decade is the decade of Internet of Things and artificial intelligence. Well, it is, as if we look at this historical evolution, the number of connected devices, wireless connected devices, is literally exploding, and the state of the art of artificial intelligence and machine learning, it is still conceived for this stage of historical evolution of technology, where data is collocated, is clean, immediately available, without delays, without communication bandwidth restrictions. But this is certainly not the case of wireless Internet of Things, when instead here data is distributed, and the data analysis that has to be done at this point depends a lot on the data that is generated by other devices, and it's difficult in general to send this data, to transmit data over shared wireless communication systems, especially because these are public wireless communication network. So we need new theory methods to work with artificial intelligence and the wireless Internet of Things. From a more now researcher point of view, the problem of machine learning over wireless networks is in general concerned with the problem of performing distributed model training and distributed inference at various wireless devices, which are connected through some cellular communication system. And in general, the data analysis, that is model training and inference that has to be done here, depends also on the data that is generated by other devices. And what is difficult due to the challenge that we have mentioned before is that we cannot send all the raw data directly to some parameter server, to some access point or base stations, but instead we have to have distributed machine learning method, distributed computations. And the wireless communication here play a very important role, since the communication on this link is wireless. And again, from a research point of view, wireless and machine learning generate three main research areas that we have portrayed here with this figure. One is called machine learning for wireless, and this refers to that we can use machine learning to redesign from scratch wireless communication protocols, as opposed to use instead a model-based design, which we have used more or less until so far for wireless communication protocols. The second area instead is to distribute machine learning services when the underlying communication network is wireless. This is already happening in many research domains, and in particular, it is a prominent area here, which is the one that is called edge artificial intelligence. And the problem here is to essentially make aware machine learning of the fact that the underlying communication network is wireless, so that distributed machine learning method can work despite the fact that there is a wireless network underlying. And then the third area, which is instead this one here, and is the area that we are covering with this tutorial, is wireless for machine learning, which in a sense is a little bit the reverse of the other areas. Here, the main concern of wireless for machine learning is to redesign and to augment, to improve, or really redesign from scratch wireless communication protocols so that they can support machine learning services. Because performing distributed machine learning of a wireless communication network has the challenges that we have mentioned before, and those challenges, they are not well considered in the state of the art of wireless communications. We know that it's possible to show that the usage of wireless communication protocol as they are considered today can be very inefficient for supporting machine learning services. So the topic of this tutorial is to give an overview on the state of the art of what has been done in the area of wireless communication theory when wireless methods at the physical layer and the medium access control can have to support machine learning, in general, artificial intelligence services. And again, the main point of view is that the state of the art of, existing and even commercially available and standardized wireless communication protocols, these protocols are yet far from being able to tackle the challenges that we have mentioned before. The challenges in terms of energy, bandwidth, delay, security, privacy, distributed nature of the data sets. And therefore, we argue that we need fundamentally new wireless communication protocols and methods to support machine learning services, which is what we are introducing today with this tutorial, which is arguably one of the very first, if not the first, tutorial that gives an overview on a number of contributions that have been researched in the recent years in this domain. The tutorial is organized across these 5 main sections. First, we will give a primer or an overview, an introduction on distributed machine learning. Then, and this introduction is given by my colleague, José Ayrton Barros da Silva Jr. Then, after the section 1, we will have a section 2, which is on a primer on computation of multiple access channels. And this is in particular gives the background and the fundamental principles on how wireless communication can help in performing the computations that are needed in distributed machine learning. In section 3, and by the way, section 2 will be covered by my colleague, Henrik Hellström. Section 3, instead, will be focusing on computation of a multiple access channel for machine learning, where, in particular, due to the superposition principles of radio waves, we can perform the computations in distributed machine learning exploiting interference. So interference that so far is considered as an enemy in wireless communication protocol design instead becomes a dear friend when we can do machine learning or distributed machine learning. Then we will, after this, we will have a section 4, which instead is focusing on orthogonal machine learning driven communications, where the point is that the protocols that allow orthogonal access to various distributed wireless devices, these protocols can be orchestrated in such a way that they will result in better performance of the distributed machine learning, and so in less spectrum usage and more efficient communications. And this is this section 4 is given by my colleague Victoria Fodor. Then we will have a section 5 where we will try to make a sort of a collection of interesting open challenges and future research directions that are some of the important challenges and research directions that still have to be researched in the next years. And this section will be mostly covered by Josemma Ayrton Barros da Silva Jr. and by Henrik Elstrom. And after this, we will conclude the tutorial. And now is the time of the primer on distributed machine learning by my colleague Josemma Ayrton Barros da Silva Jr.
Welcome to this tutorial on wireless for machine learning. My name is Josemma Ayrton Barros da Silva Jr. I am a senior researcher at KTH Roger Institute of Technology. I'm going to present the first section of this tutorial, a primer on distributed machine learning. In this section, we are going through 3 main parts. The first one on machine learning. And here we are going to understand the basics and the fundamentals of machine learning. After that, we are going to understand distributed machine learning methods and the difference between distributed machine learning and the traditional machine learning that we see in the first section. After that, we are going through federated learning methods, which are a type of distributed machine learning methods that is heavily popular today and that will be used a lot throughout this tutorial. As we know, machine learning is a huge research area, and we can categorize machine learning in 3 different categories mainly. First one is unsupervised learning, in which you are trying to learn from a data that is unlabeled. So we don't know what are the different categories of this data. And here, one of the main goals is to identify the data distribution. And K-means is a very prominent example of unsupervised learning methods. Then we go to supervised learning methods. Now we have data that is labeled, and we use this labeling mainly to get expressions for regression and classification problems. These are other categorizations within supervised learning. In regression problems, we have real valued problems that we are trying to predict. And then in classification problems, we have variables that are categorical. So here we want to classify the data that we have within these categories. And a main example here nowadays is the use of deep neural networks as supervised learning. Now, different than these 2, we have reinforcement learning. And with reinforcement learning, we are learning by interacting with an unknown environment. And usually this environment is modeled by a Markov decision process. Here, a prominent example of this learning category is Q-learning. And within this Markov decision process, we have a sequential decision making. But one problem that we have here, or challenge, let's say, is the lack of a correct data set a priori. So with this, we are allowed to do suboptimal actions during the learning process. So here, within these 3 different categories, we also have some overlapping between them. And we are not going to discuss them, but In this tutorial, we are mainly interested in supervised learning techniques. And in supervised learning, we have here an example. We have here a photo of a cat, picture of a cat. And this is the data that we have, which is labeled. Then we are going to use this data as input to an inference function, GW of X here. And in this specific situation, this inference function is given by a neural network. And then using this prediction function, we get the Y here, the label that we desire, which is the output. And then using this specific model, we get that this is a cat with 99% of confidence. So as I said, in the following, we are restricting ourselves to supervised learning. And to do that, we need to give the main definitions of a supervised learning problem and how do we model these problems and how do we solve these problems. And that's what we are going to see now. So here we are defining first the loss function and the expected risk. So for now, consider a data set D, and we have the input here xi and the labels yi. And then we assume that these labels have some inherent function here, age of xi. And we assume that we have n training samples. Then what we are trying to do is to perform a prediction, so machine learning prediction, this y hat. And to do that, we use this inference function, GW of X. And by using this W, what we want is we want to design, to train a model to have a good prediction function, GW of X. And notice that this function here is a parameterized function over W. And then once we choose W, we also need to define a loss function. And then this loss function depends on X, depends on h of X, which gives the true output, Y here. And also the prediction function that we are using, GW of X. And then our goal here, the objective, is to minimize what we define as expected risk or the expected loss between the prediction and the true output here. And that's what we have here in this equation. Here we are defining the expected risk. We depend on the loss function. We also use here the loss function, which depends on h of X. And now we are parameterizing that over W. And then we compare that with the true output, Y. And notice that here we have the expectation. And this expectation should be taken with respect to the true distribution of X and Y. So we say also that this minimization of the expected risk is the test or the generalization error. But here we see a fundamental problem or difficulty, let's say. The problem is that here, as I said, we need to use the true distribution to obtain this expectation. But this true distribution, the probability of X and Y is unknown. So how can we solve this problem? How can we minimize this expected risk? So a way to do that is to define the empirical risk. And here we use the empirical risk as a measure of the expected risk. Here we have the empirical risk being defined 1 over n, and n is the total number of samples that we have. And then we sum over fi of w. And then this fi of w is just the loss function that we have using the prediction function depending on w over y here. And notice that this is a sample expectation. So now instead of using the true distribution that we had before, we are using the data that we have. So the expectation is taken with respect to the data sets, to the n samples that we have. So we can understand this empirical risk as an approximation of the expected risk. And then we define this minimization of the empirical risk, or the minimal empirical risk, as the training error, which is an estimation of the test error. And notice that these two are different. So in practice, what do we do? In practice, we minimize the empirical risk. So ultimately, we'll choose or we'll train W and obtain this prediction function, T of W of X, as the result of an optimization problem. This optimization problem, to be more specific, we are minimizing the empirical risk here using N samples for this specific W, and then this W belongs to a specific set, W calligraph here. And that's what we do in practice. We use the empirical risk and we minimize this empirical risk and obtain the W that minimizes that. So how can we solve this optimization problem? And that's where we get the first training algorithm, which is the gradient descent. So to obtain the model W, we solve this optimization problem. And a solution to this optimization problem is using gradient descent or batch gradient descent. So here, to solve this, we consider that for the next, we have an iterative approach. WT plus 1 uses the previous update. And now we use gradient information of the loss function, f of I, evaluated at the previous point. And here, notice that this is used for all samples, and that's why it's called batch gradient descent. And also, we need to define a training parameter here, eta, which is chosen appropriately for convergence. And here, f of I is a composition of the loss function evaluated at the sample I. And then we can prove that this algorithm converges to the optimal solution of the model here, the W prime, let's say, under some assumptions. We are not going into the details of this convergence, but just know that it converges under some assumptions, which depends on the gradient, the loss function, and also on the training parameter eta. So now we have seen the batch gradient descent, but usually that's not the one we use in practice. What we use in practice is what we call stochastic gradient descent, SGD. And SGD is a noisy version of the gradient descent. We can define SGD into this general form. We have the update here, the new WT plus 1, considers the previous one, minus the eta parameter. And then here, different than the full batch gradient, we have G of WT, and then this T over T. What is this T over T? This is the seed for a sample pair of X and Y, which is chosen randomly from the set of samples. So notice that this G of WT using this sample is a noisy version of the gradient that we have. And this noisy version can be just for one sample, so just one T of T. Or we can also have what we define as a mini batch of some specific size here, NT. And then we are picking a subset NT randomly from this subset 1 until N. And then we evaluate the WT plus 1 considering only this mini batch. So as you expect, we can also prove convergence to the optimal solution here. And it depends again on some assumptions. And we can also bound the variance of the error that we get here of this noise. And here, to decrease the variance of this noise may give some improvements. And some variants of that include SVRG and SAG. We are not going into the details of SVRG and SAG, but you can find some of these references into the main paper that we are referring to that is based on this tutorial. So here we have SGD and batch gradient descent. So what is the difference between them? How can we compare these two? That's what we have here. So in batch gradient descent, usually the per iteration cost is very expensive because remember, we need to evaluate the gradient for all the samples here. So usually the per iteration cost is linear in N, in the number of samples. And one very good advantage of batch gradient descent is that we don't need many iterations to obtain convergence. So usually few iterations are sufficient. If we go now to SGD, the per iteration cost is very cheap because remember, it does not depend on N. It can be just one sample or just a very small mini batch of this whole set defined by the number of samples. But when we go to the number of iterations, we may need more iterations to converge. Because remember, this is a noisy version of the gradient descent. So here, the main trade-off that you need to consider is the per iteration cost versus the per iteration improvement that we have. And in practice, when using deep neural networks and some other models, we use a lot SGD instead of the batch gradient descent because the per iteration cost is just overwhelmingly more important than the per iteration improvement. Okay, so that was our main discussions on fundamentals of machine learning. Now we are going to distributed machine learning and also the differences between the machine learning that we have just learned. So the machine learning that we have seen is what we call centralized machine learning. And in this situation, we have here some devices, let's say device 1, 2, until device K. These devices, they have their own data 1, data 2, and data K. And we also have a cloud server here. And then these devices, they transfer this data to the cloud. And then the cloud performs the training. Here we have an example of a neural network being used. So at the cloud, we have the training and the testing. And also the inference and the predictions, they need to be fetched from the cloud. So here, after the training is done at the cloud needs to send back to these devices the inference and the predictions that they may use for their own activities, their own applications. So that's what we have seen before. We have a centralized server that takes care of everything, that also gets the data and trains and tests the model at the cloud. So the devices, they just send the data. This is remarkably different than distributed machine learning. So here we have what we call now a parameter server. And the parameter server is also responsible for some activities, but the main difference is now that the devices, here device 1, 2, until K, they have their own data. And usually they don't send this data, but they just send an update of the model here. For instance, here's some weights of the neural network. So they send these updates of the neural network to the parameter server. And then the parameter server may do some other training and send back an update over that. And here, this parameter server, you can think of this as a base station or an access point. So usually this parameter server can also be an edge server. So not just a cloud server. So here, usually the data and the training can be distributed. So the devices, they may send the model here, these neural networks, or they can send the data as well, depending on the technique that you are using. So which is very different than before. And also notice that the devices, they may communicate between each other, just something that we didn't have before. And also, as I mentioned, the training and the testing happens at the devices here, or at the parameter server. Even the parameter server can do some updates together with the devices. So it's much more flexible than the centralized machine learning. So now distributed machine learning is a very big field. And within this field, we have two different categories, which will be important for us to discuss. So these two categories are the following. So first, here we have the centralized architecture and the decentralized architecture. In the centralized architecture, we have the devices, they have their own data. And usually they send the model here, these model updates. They may also send the data, the parameter server. But notice that here the devices, they do not communicate with each other. So the parameter server still holds some power over the devices such that the parameter server is trying to coordinate with the devices. So the devices do not communicate with each other, which is different than the decentralized architecture. So here, the communication between the parameter server and the devices is allowed. So that's the main difference that we have between these in the architectures of distributed machine learning. In this tutorial, we are mainly focused on centralized architecture, because remember, we are in a wireless communication scenario, and usually the access point or the base station controls the communication. So that's why we are mainly considering here the centralized architecture. But you can also consider the decentralized architecture as well, using some device to device, let's say. So in distributed machine learning, we have many recent results. So here we have some 4 examples of techniques that are very popular today. The first one is federated learning. Here, this is the seminal paper of federated learning, one of the seminal papers of federated learning. Then we have what's called FDML, so feature machine learning for distributed features, which was recently published at the KDD. And then we also have the COCOA algorithm, which is a very general framework for distributed optimization and also provides a lot of benefits in terms of communication efficiency. And finally, we also have DNNC, which is distributed deep neural networks over the cloud, the edge, and the devices. And notice that all these references, they are, let's say, quite recent. So there's a very hot field. And in the following, I'm going to present you some differences between these and how we can make a high-level classification for distributed machine learning methods. Another classification that we can make is the following. So first, we can have distributed data. And a prime example of this is federated learning. So here we have the data on the y-axis and then the features on the x-axis. So here, some data, they have all these features and then some other data, which are from different, let's say, category. They also have the same features. And then these devices, they train differently these data. But ultimately, we use a master model or a global model together, and we have some interaction between these different devices using these different categories of data. And here, notice that we have a common master model. So here, this applies when all devices, they need the same model, the same global model. A difference from this is distributed features. So now instead of having this distribution over the y-axis, we have over the x-axis. So here, all the data, they have different features here. But some devices, they have only a specific feature here and only specific feature. So this is a prime example of FDML on the distributed features. And similarly, we also have a master or a global model that we train together with these devices towards a common goal. And here, this is important when the devices, they observe different features. And finally, we have here a distributed model in which the inference is distributed among the devices. So here we have a neural network running over some parts of the model, some of the features and the data, and then some other neural network on these devices being run. And then ultimately, we use together these two devices and build the complete deep neural network model. And this is also an example of DNNC and COCOA. So remember, here we can have the data being distributed, the features being distributed, and the complete model being distributed. So now we have understood the differences and the categories within distributed machine learning. We will now make some definitions of distributed machine learning and see how the empirical risk changes from the traditional machine learning. So now the samples, they are split at k different devices. And we consider that the device k holds this data set, dk. And we assume that this device nk is the total number of samples at device k. So globally, our objective is to minimize the empirical risk, just as in traditional machine learning. So here, this expression is the same that we have seen before, but now we have a difference here. Fk is the local empirical risk, and notice that here we have some scaling factor as well. And then this Fk is what we call the local empirical risk. And this local empirical risk is evaluated over the local data set here. So in this figure, we have some devices here, each with their own data and their own local empirical risk. And then they are exchanging here with the parameter server the gradients with the model, and then they are receiving an update of this gradient. So this parameter server can run an algorithm, more iterations over all the gradients of the server, or can do a simple scaling of all the gradients. That will depend vastly on the technique that you're using, on the distributed model that we're considering. And here, notice that we have a common global goal, which is the minimization of the empirical risk. But that is done locally here. And by each local iteration, we want to arrive at the minimization of the global empirical risk. So here, what we also need to discuss is that we consider that the data sets are independent and identically distributed. Why? Because once we consider that, we can prove that the empirical risk over their own data sets here, using the local empirical function, is equal to the global empirical risk that we have seen here. So notice here the importance of having samples that are IID. If the data sets, they are non-IID, then this approximation here can be arbitrarily bad. And that's very important to keep in mind, because in practice, we may not always have non-IIDs. We may not always have IID samples. In fact, most of the times we have non-IID samples. So after all, to obtain the model W, each devices, they use one SGD iteration, and they can exchange the updated weights between them or the parameter server. And notice that here, this is also general to consider both architectures, centralized and decentralized. After that, the received models, they are aggregated at the parameter server, average, and they can also be used as input for next iterations. And together with some of the methods that we discussed before, some specific methods for this optimization include distributed stochastic gradient descent, consensus optimization, also ADMM, which is widely used in wireless communications, and also the COCOA method that we discussed before. So we have understood now distributed machine learning, and we can see that there are some challenges that we can discuss. The first one is the communication efficiency. So we may have a lot of devices, and these devices, they need to exchange information between them or between the parameter server. So we need to pay attention to the massive number of messages that they need to exchange. And also that these messages, They may also bring a lot of latency, and with this high latency, they may also increase the convergence time, which is also a problem for practical uses of distributed machine learning. Now, we also have a problem on systems heterogeneity. So the devices, they have different storage, computing, and communication, and also different number of samples. So we can imagine that we have a very cheap sensors being used to collect some data, and they can also use distributed machine learning to do some training with very technological iPhone devices, some phone devices. So that's widely different storage, computing, and communication capability. The other point is what we define as statistical heterogeneity. So here the devices, they have different distribution of the data. And as we have seen before, we can have non-IID sample distribution, and that may as well destroy the approximation that we want to obtain. And finally, we also have a problem with privacy. We need to ensure that these communications are happening in a private manner. So the devices, they may need to send sensitive data across the network. For instance, the raw data or also the full gradient. And this data needs to be private from the network and also from eavesdropping or some other agents that may use that. They want to use that data for other applications which are not intended by the device. So with these challenges, we'll discuss now a technique that tries to overcome some of these challenges. And this technique is federated learning. So now we are going to discuss federated learning, and federated learning was mainly proposed as a way to overcome some of these challenges. So here we have a very nice comic from Google. And here we, as before, we want to train a centralized model using data that is decentralized. So the devices, they have their own data. And one important feature of federated learning is that the device, on-device data is used to train a model at the device, and the device does not need to transmit that data to the server. So then what federated learning is doing is that it's bringing the training to the device and transmitting the model updates instead of the raw data. So these are the key features of federated learning. We are training a centralized model on decentralized data, and we do that by training locally at the devices, and we do not send the raw data. We send the model updates to the parameter server. And with this, we are trying to overcome the challenges that we have seen before, the communication efficiency, the privacy, and also here, specifically the systems heterogeneity. And we'll see also some discussions on the statistical heterogeneity. So now let's discuss about some fundamentals of federated learning. We consider that we have a subset of devices, ST, which is sampled from the K devices that participate on a specific round. So you can have thousands of devices, but we are using just a small subset, ST. And this selection criteria can be random or based on other criteria. For instance, you can use the importance of the gradient or some other probability decay. And then each device solves a local empirical risk problem here. This is the SGD update that we have seen before. And then this device sends the solution WKT. And here notice that K is the index of the device. T+1 is the index of the local of the local update. And then this device will send the solution WKT to the parameter server here. And then the parameter server holds a global model here. And then this global model is simply an average aggregate of the local models of the devices that are participating in the training. So here, we are just adding up the WKTs that we received, weighting them here based on the number of samples that each device holds, and summing only for the subset that we have selected. And then once the parameter server does that, it sends back here, WT, back to the devices. So notice that the data stays at the device, and the devices only exchange the final model update here. And notice that here, this solution of the empirical risk, this is just for a single iteration, but you can do for many local iterations. Okay, you'll see that in a moment. So to summarize federated learning, we have here a lot of devices. So devices 1, 2, and 3, K-1 until device K. These are the data that each device holds. And these are the local models that these devices have. And then this device 1 has been selected to communicate. We have here the strong arrow. This device has not been selected. This device has been selected, and device K as well. Then this local update, W1/T, is transmitted to the parameter server, the same with W3T, and the same with WKT. Then the parameter server will average this weight here, and here specifically only for these devices that are participating in the training. And notice that here we have the whole subset of K, but just remember that we are assuming that this device is not transmitting anything. So then this is just making an average, just considering this as 0. And then once the parameter server averages the weights from all the devices that have been selected, it sends back this global update for the next iteration for WT+1. So notice that this WT+1 is sent back to the devices. And in this specific situation, it can send back as well to the devices that have not participated in the training. So device 2 and device K-1. So this is a general overview or a summary of federated learning. You discuss more about the details of federated learning. So as I mentioned before, every device runs SGD, but these devices, they can run several iterations locally. And we call these local iterations, we say them as E, and we name them as epochs. So usually these epochs are used for local iterations, and then we term T as the global round iteration. So here, instead of using just one SGD as some other distributed machine learning methods, we are running for a number of local iterations. And also you need to tune the number of local iterations that you may run, because you may also run into some overfitting for this specific data of these devices. So overall, a measure of convergence for federated learning is the following here. So we are comparing the loss function, the global here, expected risk, or the empirical risk, sorry, WT+1, let's say the last iteration between the previous iteration over f of WT. And then we compare this difference in a norm, specific norm. And then we define that this model has converged once it is below some predefined epsilon value. Another way, which is also popular, is to bound the total number of global iterations that we have T. So then you can run this for, let's say, T equals to 200 global iterations. But this is the mathematical measure of global convergence. So now, since we have defined federated learning, let's discuss the first algorithm of federated learning, which is called the federated averaging. So this federated averaging was proposed in this paper, which is the seminal work of federated learning here, which was proposed by Google. And then in federated averaging, we consider that the devices, they are indexed by K. We consider that B is the local mini batch size. E is the number of local epochs, and also the client selection, select some C here, fraction of devices. And eta is the learning rate that we have seen before. So then here we have two different parts of the algorithm. The first one is executed at the parameter server. The second one is executed at the device. So at the parameter server, first we initialize the global model W0, let's say. Then for each global round T, one until convergence has been achieved, we pick the devices. Here we pick a number here using the percentage here of fraction to be selected the devices. Then we randomly select M clients from out of K. And then with this, we have defined the set ST. And then for each device into this set, we do in parallel the device updates here. Then at the device, let's say for device K, we have to define, to initialize B here, which is the split of the data set into these batches of the data. Then for each local round or each local epoch, we do the batch update here. And here we have the SGD update for each device. And once this is done for the batch, and also for the total number of epochs, we return this W to the server. And once this is done, go back here, the server gets this W, and then does the global aggregation step, which is basically an average over the devices that we have selected here. So notice that here we have three phases. The first one is the device selection at the parameter server. Then we have the device update, which uses SGD. And then we have the global aggregation. So overall, this is what the federated averaging algorithm is doing. So federated averaging was proposed in 2017. It appeared before on arXiv. But since then, there have been many updates to federated averaging. There are many other federated learning algorithms that use different client selection, that use different device updates, and even in some cases, different global aggregation. So this is just the pure federated learning, the first one. So then we also have some extensions of federated learning to mitigate some of the distributed machine learning challenges, because the literature has seen that pure federated learning using federated averaging was better than others, but still some challenges need to be addressed. So here on the communication efficiency, we have different optimization methods that are used to reduce the number of communication rounds. And on another direction, there have been also methods that use sparse or quantized model updates. So because let's imagine in a big data scenario, the model updates that you need to transmit to the parameter server can be gigantic. So you can sparsify that or quantize. And then for the system heterogeneity, you can have different local optimization for the devices. So let's say, for instance, that you can have different number of local iterations depending on the device capability, and also different size of the batch, depending on the capabilities of each device. And then regarding statistical heterogeneity, some other optimization methods have provided convergence guarantees for non-IID data distribution. And this can be seen in some other papers that we have cited into the survey. And finally, on the privacy loss, because even though we are not transmitting the raw data, we are transmitting the model updates. And to make that further private, we can use differential privacy and also secure aggregation methods to ensure the privacy of what we are transmitting. And you can see some of these extensions also into this paper here on arXiv, and I suggest you to do that if you're interested. And federated learning is changing a lot across the recent years, and it's a quickly evolving field. And now what we are going to discuss is how that is tied with wireless for machine learning. Thank you.
Hello and welcome to the third part of this tutorial. My name is Henrik Hellström. I am a PhD student under the supervision of Carlo Fischione and Victoria Fodor, and I will be giving the next segment of this presentation. Now that we have finished the primer on distributed machine learning, we're almost ready to move on to our main topic of wireless for machine learning. However, before then, I'm going to introduce a wireless technique known as computation over multiple access channels. This is a technique that is fundamentally different from the traditional wireless communications we have today in the sense that it promotes interference instead of avoiding it. It's something that has seen frequent use within the wireless for machine learning literature, and it can offer some significant benefits. It's also known as over-the-air computation. We will be using these two names interchangeably throughout the presentation. Now, we consider a network that consists of k devices and one parameter server. All of these devices can reach the parameter in a single hop, as indicated by these arrows here, over a multiple access channel. We also consider a scenario where each device is carrying its own data set. And if we're using a machine learning technique such as federated learning, they will all train their own local models, WK, at the devices. The goal of the network is to reconstruct a function of these local models at the parameter server. In this case, we're looking at an arithmetic mean. So this R here is going to be reconstructed at the parameter server. Now, this goal could be accomplished using the wireless networks we have today. We could allocate orthogonal radio resources to each of these K devices and let them transmit their WK up to the server. After the server has received all of the WKs, it could then compute the arithmetic mean locally on its own processing unit. As an alternative to this, over-the-air computation considers the computation of this mean in the air itself. So the goal is to shape the waveform in such a way that when the waveforms collide in the air, they will naturally calculate this arithmetic mean. So, as I mentioned, we are able to accomplish this goal using traditional wireless communication. So why would we want to make this radical change? Well, the benefit is that we can utilize the bandwidth much more efficiently with over-the-air computation. As we all know, orthogonal multiple access protocols such as TDMA, FDMA, and OFDMA divide the radio resources between the users. For instance, in TDMA, each device is given its own time slot to transmit its local updates, and we cycle through all of the devices until all of the capital K updates have been communicated to the server. Alternatively, we could use, for instance, FDMA, where all of the devices can transmit simultaneously, but the bandwidth is divided between the users instead. So in theory, both of these protocols should take the same amount of resources to communicate the updates. However, in over-the-air computation, all of the devices communicate simultaneously over the same bandwidth. So we don't have this division of radio resources that we do with an orthogonal scheme. This also means that we can communicate this entire arithmetic mean in about 1/k of the time or the frequency, which we could do it with an orthogonal scheme. So we will experience approximately k times higher spectral efficiency with over-the-air computation than we do with an orthogonal scheme. I'm saying approximately here because it depends a little bit on the network setup, but it's going to be around that range. And this spectral efficiency can be crystallized either as a latency reduction, as we see here, the time is now much shorter, or it could be crystallized as a bandwidth reduction. We would only have one of these bars in FDMA to calculate the whole arithmetic mean. Now, with over-the-air computation, any nomographic function could be calculated over the air. And here I'm giving some examples of important nomographic functions that see some use in practice. We already mentioned the summation or the arithmetic mean function. We can also mention multiplication, And finally, you can also do something like maximization or minimization, although this is an approximation, will not be guaranteed to find the maximum value. An important thing to notice here is that individual sample reconstruction is not possible. So the server will never see all of the individual WKs. It will directly experience this function that has been calculated in the air. So if your application for some reason needs this individual WKs, then over-the-air computation is not applicable. In addition to this, we will have imperfect reconstruction. And the reason for this is that over-the-air computation relies on analog communication. That's how it's able to shape the waveforms to get the function that we want when the waves collide over the air. An analog communication means that we have no forward error correcting or error detecting codes. And additionally, the function estimate at the parameter server will always have some level of noise. So if you're using over-the-air computation, you have to accept that you're not going to see the exact function that you're looking for, and there will be some sort of estimation error. So with this in mind, what are fitting applications for over-the-air computation? Well, one important thing to notice immediately is that we cannot reconstruct individual WKs. So if we're thinking about, for instance, text messages, you would never want to compute this with over the air because it's not enough to get a function of many different people's text messages. We need the exact text messages so we can forward them to the right user. But there are applications where just a function can be enough. For instance, in sensor data aggregation, we're often only interested in, for instance, a maximum sensor value or an average sensor value to take some action rather than all of the individual sensor values. We can consider distributed consensus. For instance, in fleet control of vehicles, often it's enough to see the average velocity and direction of a vehicle rather than knowing the individual velocities and directions of all vehicles. And finally, we can consider federated learning over wireless networks. Because as Merton has mentioned in his primer on distributed machine learning, the update step of the federated learning algorithm doesn't actually ever need these individual updates WK. It only needs this arithmetic mean, which is one of the functions we saw can be calculated over the air. Now that the introduction to over-the-air computation is complete, I hope that you understand the basics of the technique. To reiterate, over-the-air computation promotes interference, as it is leveraging this interference to calculate a function over the air. The benefit of using such a technique is that we can get very high spectral efficiency. However, the technique also has its downsides. Since it is using analog communication, we cannot have forward error correcting codes at the transmitters or error detecting codes at the receiver. Therefore, we can't expect to get a bit perfect reconstruction at the server. What I didn't talk about in the introduction is how these protocols are implemented in practice. And to do that, I'm going to talk about the estimation error, because the way the estimation error is dealt with gives a good insight into how to design such a protocol. At the top here, you can see a block diagram for a multiple access channel. If all of these devices are perfectly synchronized in their transmission, then the wireless channel is naturally going to superimpose these signals to calculate a sum. So even without any sort of pre or post coding, we will have a weighted sum of these W's at the receiver. In addition, we have a noise component that goes into this addition on the top here. After the server receives this R, it will divide it by capital K, since we're interested in the arithmetic mean rather than the sum. Now, because of this fading and additive noise, we get a mismatch between the desired function, which we have here on the left, and the received function, which we have here on the right. The biggest problem is that these channel gains are going to create a weighted sum of the WKs rather than the clean sum that we are expecting here. To deal with this problem, we generally consider a precoder. So we add another scalar bk here that the devices multiply with their W before making the transmission. If this precoder is selected as follows, then you will get rid of the complex part of the channel, and you will only be left with this magnitude or the gain of the channel in the end. Additionally, this power component PK here can be selected to completely get rid of the effect of the channel. So assuming that the devices know the channels before they are transmitting, they can select square root of PK to be 1 over the magnitude of HK. And if we do this, we see that this sum up here becomes a much nicer sum down here to the right, which actually has the correct sum on the left side with this additional noise term on the right. Now this sum here is quite nice because the only problem left, if we compare this to the desired function, is the noise term, but the noise term is divided by capital K. So generally this is going to be quite low. However, there is still a problem left here, and that is that this power can become incredibly large. If one of these devices is in a deep fade, HK can be a very small number, and this division is going to cause PK to be very big. And in reality, the transmission power is limited. So how do we deal with that? Many papers consider it basically as a device exclusion. We were just saying that if you do not have enough power to invert your channel, then you will not be able to participate in the over-the-air computation. However, recently there have been some works on using power control to get a better solution than device exclusion in terms of the mean squared error. For instance, we have this paper by Xiao and Xiao that was recently published. We showed that for our network setup that we consider in this presentation, you can actually find the optimal power control scheme in a closed form. Their scheme showed that there basically exists a threshold, and all of the devices that have enough power to invert will be on the right side of this threshold. So here we see that the transmission powers for the channels, for the devices with good channels, they're going to be able to select the transmission power which inverts their channel. Of course, these powers are all different because they will depend on what channel that you got. However, instead of excluding the devices that are not able to invert their channel, they simply let them transmit with full power. And doing this gets them closer to transmitting the actual value that they want to transmit, even though we're not actually going to have this nice sum term here on the left. As we can see in this simulation slide here on the right, this optimal power control is strictly better than traditional channel inversion in terms of the mean squared error. For the final part, I'm going to talk about the interaction between over-the-air computation and federated learning. In the first two parts, we learned about some interesting properties of over-the-air computation that are not present in a digital communication scheme. And now in the final part, I want to talk about what implications these properties have when you're training a machine learning model. Additionally, I'm also going to more clearly describe how over-the-air computation is used together with federated learning. As we have previously described, federated learning consists of a number of communication rounds, and each round begins with a parameter server broadcasting a global model down to the user devices. In this broadcast step, over-the-air computation is not used, but we use a digital communication system there. However, for the uplink aggregation step, where these trained local models are going back up to the server, this is where the proposal is to use over-the-air computation. If we go back to what the parameter server are doing with these model updates from the user devices, then we see that they're actually only using the average update at the server. They never need these individual WKs to generate a global model, just this arithmetic mean is enough, which means that we can use over-the-air computation to generate the global model. However, remember that there is an estimation error introduced with over-the-air computation. So there could be some worry here that by communicating over the air and getting an error here on the global model update, that we're harming the convergence of the machine learning model. In this paper here by Guangxu Chu, he is comparing federated learning with over-the-air computation to federated learning with digital communications. The solid blue line here is the accuracy of a system using over-the-air computation, and the green dashed line is a system using digital communications. And indeed, we see a slight drop in accuracy when you're using the over-the-air computation system, but it's not that significant, and we see that there is a comparable level of accuracy between the two systems. However, when you look at the latency, we see a massive improvement when we're talking about over-the-air computation. For this particular setup, we have between 1 and 3 orders of magnitude lower latency. In this slide, I have listed out some advantages and disadvantages of choosing over-the-air computation. The first fairly obvious advantage is that we have the potential to get orders of magnitude lower radio resource consumption. Since the communication is often a bottleneck for federated learning systems, this is a very important benefit when you're training over a wireless network. The second advantage is a bit more subtle, and it has to do with differential privacy. Now, when you transmit a model update to the server, there is a risk that your model update reveals a lot about your dataset. So if you want to keep your dataset private, then you might actually be giving away some information by giving the server your model update. The field of differential privacy is analyzing how this can be mitigated. And one of the ways to do that is to artificially add some noise to your model update. What does this mean? Well, it means that this estimation error that we get in over-the-air computation is not necessarily a downside. We could actually see this as a blessing, as it's increasing the privacy of the system while not harming the accuracy that much. Finally, we know that the server cannot determine who is participating in the training. Since the server will never see the individual model updates, but only see this mean, it's very hard to interpret any kind of information about the individual device's datasets. So let's imagine that the differential privacy is poor or that the noise is not enough so that they can actually get some information using this model update. Well, they still wouldn't know which device that data is coming from. The only information it could possibly get is something that is regarding the mean of the dataset or kind of the sum of the data between all of the participating devices, which is of course less incriminating. However, this final property here could be seen as a blessing, but it could also be seen as a curse, because if it's impossible to determine who is participating, that opens it up for adversaries. So if you have an adversary that comes in and wants to poison your machine learning model, it can just transmit nonsense weight vectors back up to the server, which is going to completely ruin the convergence. Secondly, the protocols are fundamentally different from our digital communication systems, and as such, it may be difficult to implement it in standard chipsets. Of course, if we have to replace the standard chipsets of every mobile device, then this might be infeasible, or it's going to at least be extremely expensive to implement. There are, however, some saving properties here that we will talk about later in the tutorial. Finally, there are very high demands for accurate synchronization. Even if the devices are have poor synchronization of just half a block or just a fraction of a block, that can have a massive effect on the over-the-air computation, since we're so heavily relying on this interference of the superposition of the wireless channel. With that, I conclude the primer on computation over multiple access channels, and I leave the floor to Carlo Fischione.
Hello again, and welcome to now section 3, where we will give an overview on computation over multiple access channels for machine learning. After an introduction to this general topic, I will give an overview on the computations on size of networks and then on MIMO networks. This section 3 is a direct application of what Ayrton has told us in section 1 with a primer on distributed machine learning, and of the section 2 that Henrik has presented to us on primer on the computation of a multiple access channel. So essentially, in this section 3, we will be doing over-the-air function computations for those functions that are typically used in distributed machine learning. And we will have emphasis on federated learning as an important and prominent example among the many possible distributed machine learning methods. The introduction now is again for us to remember that in traditional communication systems, such as using TDMA protocol or FDMA protocol. TDMA is time division multiple access, FDMA is frequency division multiple access. We would have to transmit the model updates of, for example, federated learning in dedicated time slots or in dedicated frequency slots. And this is what is illustrated here in this figure, where we have the models at time t and of the device 1 up to the device capital K. These two kind of figures, simple figure, again, are associated to the traditional way we could do the communication of the models from the worker or the wireless devices to the parameter server. And this is generally, it's a digital communication in its most traditional sense. But in wireless for machine learning, as we have seen before in Henrik section, we have that the wireless channel can do for us the computations for example, in federated learning, where if R at is the received signal, it can be seen as an estimation of the sum that is needed in federated learning. It's a sum of the devices of the models that the device K is transmitting, multiplied for the transmit power Bk and the channel coefficient Hk. And then at the receiver of the parameter server and in the edge server or in the access point in the base station, we have always a receiver additive white Gaussian noise V. And K here is we can be seen as a simple combiner at the receiver. Now, the central question that we have seen in Henrik section is that the federated learning sum can be done again for free over the wireless transmissions. And this is generally, it's called analog aggregation over wireless communication. And the point is that to make this sum possible at the parameter server, we need necessarily to use analog transmissions, analog modulation of this W, the model, the local model at the device K, at the worker K at time t. All this is clearly shown in this picture, can have a tremendous savings in terms of energy, frequency usage, privacy, because from the sum is here difficult to reconstruct the individual component WK at time t. But also we have many, at the same time, efficiency benefits in terms of spectrum usage. At the same time, there is many questions that still will have to be resolved here, and it's easily to think that nowadays we are most of the commercial products in 5G use digital modulations. Most of the standardized methods are based on digital modulation rather than on analog modulation to transmit this W. And the other problems is that the devices have to be synchronized. But for the moment, we assume that all these assumptions are somehow satisfied, that the devices are very well synchronized and they can transmit with analog modulation without any problem. And then now we see how this aggregation done over the channel, this analog aggregation done over the wireless channel can be possible. And it's again, the emphasis is that this kind of new communication protocols that will support this analog aggregation over the wireless channel are really new, and it's relatively few investigations that have been researching about them. So much research is still needed, again, to overcome the various assumptions, such as synchronizations or other forms of modulation. But if that one day will be possible, this is a great, it's a groundbreaking novelty in the area of wireless communication to support machine learning services. Now, this section is divided into two main subsections, one for single input, single output systems, and one for multiple input, multiple output systems. I also would like to emphasize that a general acronym used in the literature to denote this analog over-the-air function computation is COMAC, which is computation of a multiple access channels where the workers, the wireless devices, they transmit at the same time and at the same frequency. In the case of single input, single output system, we have that the received signal at the access point or parameter server is the sum over the transmitted models of the individual workers. And since it's a single input, single output system, the channel here is just a complex number in baseband signal representation, and BK equally is a precoder that is a complex number, again in baseband signal representation, and B will be an additive white Gaussian noise, again as just as a complex number. And the term 1 divided by k can be seen as the combiner at the receiver. In the case of multiple access channels with multiple input, multiple output systems, we have a multiple antenna at the transmitters and multiple antenna at the receivers. And therefore, we have to consider that the precoder B here, that before was just a complex number, is instead a vector of complex numbers where every element of the vector corresponds to the antenna elements that we're using at the transmitter. And therefore, we will have a channel matrix because of we have antenna at the receiver, and analogously we have a term at the receiver C, which is a combiner and is a vector whose size is the same as the antenna element at the receiver. And now in the rest of this section, I will give an overview on the literature about COMAC, computation over multiple access channel with analog transmissions for the case of single input, single output systems, and then for the case of multiple input, multiple output systems. So now we are focusing on this subsection, SISO networks. There is here a series of very interesting publications that in the recent years have appeared, again, specifically for the SISO and for the MIMO systems. And we have grouped these publications in this table, which you can find in the paper authored by Henrik Hellström and the others of us who are giving this tutorial today. And the paper you can find on archive in Wireless for Machine Learning. The references also are taken from the paper, and we have maintained the same numbering of this reference for the paper, so it's easy to read further. And for those of you who will have time and interest to further deepen the tutorial, you are welcome to read this paper, where again you can find the identical numbering of the references. Now let us focus again on the SISO section, and we start with the most general method, broadband analog aggregation, presented in the paper 20, where the idea is to do federated learning using communication of multiple access channel with broadband channel having truncated channel inversion to handle the fading. In particular, and now this arrow says that we will be looking at this paper here, this green arrow. In particular, the general architecture is the one of federated learning, which we have seen in Mailton section. And we have a number of devices or workers, wireless devices, each having its own data. And according to the federated learning algorithm and procedure, every device is computing a local model W K of device K at time T. Then these models are transmitted over the air with a SISO network, and at the receiver they are combined with the principle of over-the-air function computation, which we have seen from Henrik section. And look at here, the models are transmitted with a transmit power BK, which is simple in this case in the size of system is a very simple precoder. It's a complex number. And then the individual transmissions, of course, are attenuated by the individual channel HK. In this paper 84 by Zhu and others, called Towards an Intelligent Edge, Wireless Communication Meets Machine Learning, that is available from 2018 on arXiv. This is one of the first papers that proposes communication of multiple access channel especially intended for federated learning. Well, the idea is that the transmit power and in other words, the simple precoders are chosen so that they are equal to 1 divided HK. And in so doing, these two terms, they cancel each other and they become, it's just 1. They takes the value of 1. And all this under the assumption that the transmit power is high or enough to compensate the channel. And also this channel HK, in other words, the channel between this device and the edge server, it's assumed to be very well known and perfectly estimated at the worker K here, so that this compensation can be done. Of course, we don't have infinite transmit power at the wireless devices, and if the channel is too low, then 1 divided by HK, which should be the BK, would give a transmit power extremely high, which is of course not possible because of limitations in the transmit power. So the result is that we have to make a truncation in the channel for making this scheme possible. But despite this truncation that we have to do periodically, or sometimes if the channel is too low between a device and the parameter server, still we have very good performance. And in this paper 84 in particular, this is some of the interesting numerical results that they achieve. In this paper 84, there is an evaluation of the test accuracy obtained with this analog over-the-air function federated learning, COMAC in other words, in terms of using the MNIST dataset. And in this graph here, we have on the left side the number of communication rounds, the usual number of communication rounds in federated learning, and here on the y-axis the accuracy. The green line referred to FDMA refers to the fact that the devices are transmitting with digital communication over separated channels, which is not what in this section I'm speaking about, the main topic of this section, but this is for comparison purposes. What we are speaking about in this section is, in the paper, is called AirComp, in this paper 84, AirComp, that is the computation over multiple access channels using analog aggregation and with this truncated channel inversion. And as we can see, the test accuracy is quite good. So we are almost in the long run with the iterations, it almost coincides, or basically coincides, with the test accuracy obtained with the digital communication of federated learning model updates. But when we do analog aggregation with COMAC, we can see that the communication latency is significantly improved. Here on the x-axis, we have the signal-to-noise ratio for every user, and on the y-axis, we have the communication latency. The blue line corresponds to the COMAC, or AirComp, as it is called in the paper. That is, again, the over-the-air analog function computations, while the other lines, they correspond to doing federated learning with separated orthogonal channel transmissions for every worker. And clearly, since every worker has to get a resource, the number of communication resources is limited. The workers has to wait that everybody completes its transmissions. And this takes much more time. So the amount of time that we save with the over-there analog function computation is enormous, as we can see here on the y-axis. There is, however, an interesting aspect with doing these schemes, and this is highlighted in this slide here, because the point is that the channel inversion, which is achieved here by taking the transmit power as the inverse of the channel, this channel in inversion at some point is not possible if the channel H is too low because of the maximum possible transmit power that we have available. So we in principle here we have at least two options. One is that, okay, we transmit the weight, the model WK, even though the channel is very poor. We do compensation as much as possible given the maximum transmit power which we have, but this compensation will not give this product equal to 1. And in doing such transmission, we will introduce an error in this approximation, in the computation of this sum. The other alternative is that if the channel is very poor, we might decide not to select the device to transmission. I mean, the devices just doesn't send its WK, and because otherwise its transmission would introduce an error due to the impossibility of compensating the channel, since the channel is so bad. But clearly this gives, would introduce now another problem. And this is illustrated in particular in this idea somehow are illustrated in this paper 20 by Zhu and others called the Broadband Analog Aggregation for Low Latency Federated Edge Learning in the Transactions on Wireless Communication of 2019. Well, the idea is that there is a communication learning trade-off where we can decide to exclude certain devices who have poor channels, since they cannot compensate with the channel inversion cannot be possible. And the intuition now of the trade-off is given by this qualitative figure, where here, suppose that on the x-axis we report the inclusion of the devices which we have in the network, and on the y-axis we report three different things: the received signal-to-noise ratio, the data quantity that the device contribute if they are allowed to transmit, and the learning rate. We see that the higher is the number of devices, the lower is the received signal-to-noise ratio, because of increasing the number of devices increases also the number of those devices who will have a bad channel. Since we cannot compensate the channel due to the maximum transmit power, this would result in overall lower signal-to-noise ratio quality at the edge server, at the parameter server. Meanwhile, the more is the number of devices that we include, the more is the data quantity that we are exploiting, and therefore, in principle, if the communications were noiseless, we would achieve a better learning performance. But what happens is that increasing the number of devices due to the impossibility to do a correct channel inversion when the channel is bad, this will actually decrease the quality of this sum. The sum will be a purer estimation of the real sum. This sum actually is a purer estimation of the real sum when we include more and more devices, because there is the probability to have channels is increased. And so this introduces the idea that in distributed machine learning with over-the-air analog function computation, it's important to have a device selection. This part that I've just introduced is the basics of federated learning using analog over-the-air function computation, or COMAC, with channel inversion and truncation. Now, there is a series of publications that I will overview where we can do certain interesting operation on the model WK that we transmit from the devices, from the various workers or wireless devices to the parameter server. And all these papers here, they do some specific operation on these models in order to improve communication efficiency, reduce amount of information to transmit. And we start with a simple idea, the first idea, that is called gradient sparsification. Essentially here, the idea of this set of paper is that we can decrease the elements, the number of elements in this WK in the end is a vector of elements that correspond could correspond, for example, to the number of neurons in the case of deep neural network. And if these elements have a very low magnitude, then they don't introduce much information in the computation of this sum. So we can neglect some of these elements actually, but we can do in a smart manner because one can observe that the vector W, this model, has some redundancy which can be eliminated doing gradient sparsification. This idea is first proposed in the paper 73 and 74 by Amiri and others. One is machine learning over at the wireless edge, distributed stochastic gradient descent over the air, and the other one is over the air machine learning at the wireless edge. And in particular, the basic idea is that the previous methods that we have seen in the previous slide, they don't use the fact that when we transmit a WK, the model at time t of the device k, these individual models they don't contribute much. The magnitude of this gradient could be too low to contribute significantly to the computation of this sum. And in this paper, then 75, that by Amiri, Federated and others, Federated Learning over Wireless Fading Channels on the Transactions on Wireless Communication 2020, there is a comparison of doing federated learning with over-the-air function computation, analog function computation, together with the sparsification of the gradients. And in this paper, there is a comparison with many other solutions that are here on this legend, and I have reported here on the slide the meaning of this legend. We will not go through all of them, but I will just try to give the main concept. Here on the x-axis of both figures, it's reported the time that it takes to achieve convergence of federated learning. And the assumption is that there is a comparison with also digital federated learning. In other words, federated learning using a current digital communication system, not with analog over-the-air function computation. And this comparison with digital federated learning, however, assumes that the resources for communications are limited, so that there is a fair comparison between federated learning with analog on the air function computation and federated learning with digital OFDM traditional communication. Then another point here on the y-axis, we have the accuracy using again the MNIST data set, and the black line is the ideal transmission in which there is a shared link, but the communication link it's without any errors, and it's a full gradient transmissions, again without any errors and with perfect channel inversion. The red line instead is referred to the proposed scheme is this gradient specification CADSGD, as it is called in the paper 75, CADSGD. And this is the specification done on the gradients. And as we see, it's very close to the ideal transmission with the over-the-air function computation and with perfect channel inversion. This figure is referred to the case of IID data distribution across the workers, and this is to the case of non-IID data distribution across the workers. There is also then a series of comparisons. We will not go into the deep details, but there is a series of comparisons with other more basic schemes, such as instead of doing a specification of the elements of the vector of the gradients, one can do a rough quantization, even a binary quantization. And this is, for example, this curve here. Is the light blue, is this kind of binary quantization done on the elements of the vector. So it works well, but is still not as good as the specification. And then we have also to mention another method. The line here associated to SDSGD, SDSDG, is this violet line. This refers to doing transmission of the elements of the gradients without doing the quantization, without doing the specifications, but just looking at the magnitude. So the elements whose magnitude is enough is transmitted, and the elements whose magnitude is too low is not transmitted. Again, this is not performing so well, as especially in the case of non-IID data distribution, is not performing so well as the case of specification, which is this red line. Perfect. This thing said, now we can move to another operation that is done on the models WTK when they are transmitted. Before we were speaking of doing a specification of this vector, the vector of the W's at the every devices. Instead, this paper 76 introduces another method that is called federated distillation. In this case, the idea is that what is transmitted are not the models themselves, but the model outputs. And then the training is performed using this model output, and it's the model outputs that are transmitted over the air with analog over-the-air function computation. In particular, this idea is introduced in the paper 87 by Jiong and others, Communication Efficient On-Device Machine Learning, Federated Distillation and Augmentation under Non-IID Private Data. So the idea is that we don't transmit here the WK at time t, but we transmit the output of the model. So in other words, we do a local data analysis, we can say, on the devices, and this figure is taken from the paper. And at the devices, there is a local data analysis that produces a local output. Then what is transmitted over there is not any longer W, but such an output. Or as they call in the paper, is the log bits. Now, this is a significant, potentially is a significant advantage in terms of communication efficiency, because the WK can be million of elements. In the case of, for example, the well-known VGG model, we have a size of this W in terms of neurons that is 130, 140 million. Instead, if we are for example, doing a classification with just 100 labels, this D from million will become 100. So instead of transmitting a vector with 1 million elements, or actually more than 100 million elements, we transmit a vector of the order of 100 elements. Clearly, the transmission savings, it's really significant. This idea is also specifically called, the idea to transmit the model outputs instead of the model. It's called distillation procedure, and was earlier proposed in this paper 88 by Hinton and others, distilling the knowledge in a neural network that is available on archive from 2015. And now I have here some illustrative figures taken by the paper 76 by Han and others, wireless federated distillation for distributed edge learning with heterogeneous data that appeared in 2019. And here there is a comparison between the classic federated learning, FL, is the term FL that appear everywhere here in these labels, and the federated learning where we send the model outputs and not the model, which is they're called the federated distillation, FD. This D is the label that appears in these figures. And also in the labels in this figure, the A refers to analog and D to digital transmissions. So A is the analog, in other words, is over-the-air analog computation, and digital is a transmission with separated orthogonal communication channels. In this figure here on the y-axis, we have the test accuracy using, again, the MNIST data set. And here on the x-axis, we have the signal to noise ratio that it's experienced on average at the parameter server. And I will not go through all these curves, but I will only mention the most important ones. And in particular, this red one is the ideal learning, which is the learning that would be achieved in federated learning in the assumption that all the data would be perfectly available without the problems of the channel inversions and the noises at the receiver. So it can be seen as a lower bound in general. Then the other important curve is the one HFD, analog hybrid federated distillation, which is the method proposed in this paper 76 with this idea of doing a federated distillation. There is also an additional operation that they propose in the paper. Now it would take too long to explain it, but it's a further way that is a further probabilistic operation that is done on the model output before transmission. And so we can see that in particular this analog hybrid federated learning, it's quite well performing since this distillation, but at the same time reduces enormously the amount of information that has to be transmitted. And instead, the yellow lines are the classic federated learning that is the federated distillation that again is one of the methods proposed in this paper 76. And in general, this also performs quite well in terms of accuracy, also with respect to the change of the signal to noise ratio and with respect to the number of channel uses. In any case, yeah, the main message that I wish for us important to remember is that the transmission of the model outputs instead of the models can dramatically reduce the communication the communication that is needed, with a worsening of the performance that is of the order of some 1 to 20%. So one, as here, can do this kind of federated distillation operations to save a huge amount of information to transmit, but at the cost of a worsening of the accuracy. And now we move to another possible operation that it's done on the transmissions, which is the training with noisy gradients. Actually, here no particular operation is done, because in this set of paper, the proposal is to send the model of the gradients without cancelling the fading, but in other words, channel inversion is not done. And let's see what this implies. This idea is presented in the paper 77-78. It's a paper by Seri and others. One is called A Sequential Gradient-Based Multiple Access for Distributed Learning over Fading Channels, and the other one is on Analog Gradient Descent Learning over Multiple Access Fading Channels. Again, the idea is that the individual devices here, they transmit the WK at time t without doing a channel inversion, without selecting 1 divided by HK. The result, obviously, is that we could have quite a distorted sum here. Yet, it's very interesting to mention that this distortion might not have a dramatic effect. And this is also coherent in general with the behavior of with the stochastic distributed gradient descent, where the stochastic, I mean, the noise that's going on in this distributed machine learning method can have even a beneficial effect. So in this figure here, we have a performance evaluation, an initial performance evaluation of this method of doing training with noisy gradients. And on the y-axis, it's reported the estimation, in other words, the estimation error, in other words, the expectation of the difference of this term and this term here. And on the y-axis is the number of iterations. This red figure, it's the centralized gradient descent in the hypothesis that we would be able to send and the W without channel inversion, and the hypothesis that we could run centrally the gradient descent. So it's a baseline reference. Then the black line here is the one is the performance of this estimation error that is achieved with the method proposed in the paper. And the blue line is performance achieved with federated learning when we have digital communication, orthogonal communication. So this black line is the one that is interesting for us. That is the one that achieved with over-the-air function computation. And we can move to next topic. Now, another interesting activity that can be done, or a process that can be done on the models is to do a data sharing. And this is the topic of paper 79, because what we have seen so far is working fairly well when the various data sets of the various devices, they have IID data. So the data is very well represented, and so that every data set it's providing a statistically rich representation of the data for which we wish to do the data analysis. But in many situations, we have a non-IID data set. So like in this example, the digits are quite unequally distributed between these two data sets. In this case, one of the interesting idea is to introduce the concept of data sharing, which was introduced by this paper 79 by Sun and others, energy-aware analog aggregation for federated learning with redundant data. The essential idea of this paper is that the devices of the network, before doing the iterations of the federated learning, they do a data exchange, a local data exchange between them. For example, in this case, one device collects data from this device and from this device. And analogously, this device collects data from this device and this device, only two devices. In so doing, there could be a better representation of the data distribution across the devices, on top of which then we can do the usual federated learning with over-the-air analog function computation. In this now in initial study, one can see that there could be a dramatic improvement of the accuracy of the classification for classification tasks, in case this is a machine learning classification task, even between 72 to 82%. And this is one of the initial studies done in this area, because, for example, one has to try to understand what is the good number of devices with which doing data sharing, how to actually improve the efficiency of data sharing, and so on. So it's quite a number of interesting questions that will have to be further investigated in this domain. Now we jump to the topic instead of analog ADMM, and proposed in this paper 28. And I will go back to this table with the digital aggregation, but to stay on the analog ideas, analog over-the-air function computation, let me jump to this row, where the idea is that we use an alternative optimization theory method to perform the computations of the federated learning. In particular, this idea is proposed in this paper that you see here listed below, published on Archive in 2020, where the concept is that in traditional federated learning, what we try to do in general is, as we have seen from Ayrton section, we minimize a loss function using a distributed computation method, which is actually based on first order optimization theory methods. So it's a first order optimization theory method, where the first order refers to the fact that we use only the derivatives of the gradients. And those first order methods, they have a number of advantages, especially in terms of computational efficiency, because first order method only requires, again, to take first order derivatives. And they are computational light, but it's well known in general, it's a general topic in optimization theory, that first order methods, iterative methods, in particular first order iterative methods to compute the solution of optimization problem, they may require a large number of iterations, which is not good for when we do wireless communication, since every iteration means a communication round. The idea is therefore in analog ADMM. ADMM, remember, is a classic method in optimization theory that is the alternating direction method of multipliers, proposed in the 1960s and then rediscovered about 15 years ago. And instead, the idea is to, in second order optimization method, is to use also second order derivatives. And this gives another solver for the federated learning minimization problem, for the minimization of the loss function, and which, however, is more computationally intensive because of the need of evaluating these second order derivatives. However, there is an advantage that in terms of communication iterations can be much better than first order methods. These ideas are explored in this paper, and in practice, we would have an updating at the central server here, the parameter server of the global model, using this other kind of function, different from the classic one that is used so far in first order optimization method, where the main difference is that in addition to the primal variables of the optimization, the WK, we have also the dual variable, the lambda ki, and they are the ones that embed within these variables is the second order derivatives. Then in this paper, they do an evaluation of this second order optimization method together with analog over the air function computation. Remember, we are still in SISO systems. And a simple example of this comparison to get now the inside, the main message of this paper is reported in this graph. Here on the x-axis, we have the number of communications, and on the y-axis, the loss of, in other words, the minimum value that is achieved solving the optimization problem in federated learning. And here also there is the graph which reports on the x-axis the number of workers, the number of devices, and on the y-axis the number of communication channels that are used. This black dashed line refers to the ideal case in which the second order model, the second order optimization method is used at the parameter server as if the data were all available immediately. Instead, the AFADMM is this idea of doing analog over the air function computation with second order optimization method. And we see that the loss function stabilizes to low value and stays kind of constant with time. This other line instead, and the other line refers to the black line here refers to doing the second order optimization method for federated learning, where we do the transmissions with the digital communication. So it's not analog over the air function computation. Instead, the blue line is the first order method. So as you see, the first order method, which is all the methods that we had surveyed so far in the previous papers, they only were using first order method, and they are quite slow. It is also interesting to see that the number of channel uses, it's significantly reduced with this idea of analog ADMM compared to doing traditional digital communications. And there is 2 or 3 order of magnitude reductions in the sense of channel use. And now we are on the last paper of this overview on computation over multiple access channel with analog transmissions using single input, single output antennal system. And this last contribution that we wish to overview is the digital aggregation presented in the paper 80, where for the first time, as opposed to all the papers that we have been speaking so far, there is a proposal of doing aggregation over the wireless channel, not using analog communication, but the digital communication. It's still an analog communication, but it's a special analog communication. It's binary phase shift keying. And in this simple case of the digital communication, it's actually possible to do over-the-air function computation. And the idea is this, that we consider the usual system of distributed machine learning with the various data sets owned at various wireless devices. And we consider the usual iterative scheme of federated learning as an illustrative example of distributed machine learning. But what is transmitted over this communication link here is not any longer the analog W's or even the sparsified or the second order iterations as we have seen in the previous papers But instead, what is transmitted is very hard quantizations of the elements of the vectors of this vector of the gradient. And in other words, for every element of the gradient, it's a very hard quantization where we transmit either 0 or 1, and then in digital meaning. But then this 0 and 1 is transmitted with binary phase shift keying with a wave that is plus something or minus something. This idea is proposed in this paper 80 by Zhu and others, 1 bit over the R aggregation for communication efficient federated learning, design and convergence analysis, and is also based on sign stochastic gradient descent proposed in this paper 92. Let's see a little bit more the details. And here, so again, the idea is that we don't send the WK in the analog value, but we encode it with the +1 or -1 simply, and then we transmit this 2 bits information with analog binary phase shift keying. And from somehow from the modulation point of view, what happens is that at the receiver there will be a superposition of sinusoids, so that if 2 devices were transmitting 2 ones at the same time, this superposition of waves will overlap and will give an amplitude that is twice than the amplitude of the single device. And so in so doing, we can understand that 1 + 1 is 2. And analogously, if we are transmitting two waves that are in oppositions, then they will cancel out, so that +1 and -1, they correspond to the bit 1 and 0, will give as a result 0. And out of this, it's possible to still do the cohorts training in this digital, very simple digital binary phase shift keying, which actually correspond to essentially an analog over-there function computation, where there is a very hard quantization of the elements of the gradients, quantization that is just with 2 bits. And there is an interesting preliminary comparison that in this paper that I've just mentioned to you, the authors have done. On the x-axis, we have the number of communication rounds in these pictures, and on the y-axis is the test accuracy, again on the MNIST data set. And on this other figure, we have the number of devices and the communication latency. And what is surprising or very encouraging is that the test accuracy with this hard quantization in the long run is almost identical with the test accuracy that we would have achieved with the full analog transmission. That is the BAA method, the first method that we overviewed in this section. And even with transmission in orthogonal communication channels. So in other words, this digital communication in the long run achieves the same test accuracy as doing a full analog over-the-air function computation. But again, we pay is that we have to do many communication rounds. And here in this figure, instead, there is a comparison of the communication latency that is needed, and as function of the number of devices. And clearly, when the number of devices increases with the digital orthogonal channel communication, the latency increases. Instead, the proposed method, this digital aggregation method, performs identical as the analog or the function computation, and the latency is constant with the number of devices, since of course they, regardless the number of devices, they transmit at the same time and at the same frequency. And this part was about the single input, single output networks. Now we move to the multiple input, multiple output networks. Now that we have seen the single input, single output antenna model, now we can move to the MIMO case, which can be seen as an extension and generalization of some of the research that we have overviewed in this previous part. And we will consider blind learning, self-free massive MIMO, and beamforming and user selection co-design. In the blind learning, the main concept is that we will use distributed stochastic gradient descent, where the gradients that are arriving or the models updated that are arriving from the various workers can be combined with the combiners. I mean, the combiners now becomes a vector, which in a sense is introducing more degree of freedom to perform the over-the-air function computation. In particular, we have this paper that it's actually one of the very first paper on the subject of performing over-the-air function computation with blind channel estimation. It's a paper that is 94 from Goldenbaum on the channel estimation effort for analog computations of a wireless multiple access channel. It's a paper that has not in mind the immediate application to federated learning, but just to the whatever sum, whatever computation can be done in an analog manner over multi users transmission at the same time on same frequencies with MIMO systems. But this paper is very insightful because then its usage in federated learning is straightforward in a sense. And the essential concept in this paper is that if we have multiple antenna elements at the transmitter and at the receiver, then we can still perform a good analog combinations of what is transmitted by the various workers and the various devices, just having information such as the channel magnitude, but not the specific phase value, and or it's enough to have information such as fading distributions. And the concept is that the higher is the number of antennas, the less important becomes knowledge of the channel state information due to the well-known channel hardening effect. And in particular, in this paper, they consider, this paper here, 94, they consider the estimation error in the computation that is performed at the access at the base stations here, and or in the context of machine learning at the parameter server. And here on these two figures, on the x-axis, we have the error in this estimation in performing the analog function, such as arithmetic mean or geometric mean. You may remember these are functions that can be computed over there, as we have seen in Henrik's section. And on the y-axis of the first figure is the probability that the estimation in module is larger than this epsilon. And every figure here is referred to a different number of antenna element at the parameter server. In particular, the solid line, the black solid line here, is the one with the full channel state information and one antenna at the parameter server. And this other, the dashed one, as indicated, is with a different number of antenna elements. What is really interesting to see is that in the case of no channel state information and with increasing number of antenna elements, then we improve the probability that the estimation is larger than this epsilon. This figure is done for the arithmetic mean, and this other figure is for the geometric mean, but the conclusion is the same, that is that channel state information becomes less and less relevant as the number of antenna elements increases at the parameter server. These ideas, as I said from the paper that I have just mentioned, were not explicitly applied to federated learning and to distributed machine learning, but this paper here, 74, is, and in particular 81, 74 and 81, is a paper from Amiri and others on over-the-air machine learning at the wireless edge and blind federated edge learning, both from 2019. They are the ones that use blind methods, I mean, no channel state information to perform federated learning in COMAC protocols. So in other words, federated learning where the sum is automatically performed with analog computations over the air. And here, not only is performed, not only is used the idea of multiple antenna elements at the transmitter and at the receiver, but also gradient sparsification. And an interesting result in general is that there is a relation between the number of antennas and the number of the antennas at the parameter server and the number of workers. In particular, if the number of antennas is as large as at least twice the squared value of the number of devices, and this result, this fact here, then the accuracy of the federated learning over the air nearly matches the one of non-feeding channels. In other words, the one of channels with a perfect channel state information where the channel inversion is done without error. Here we have two graphs. The difference change between these two in that one is referred to the noise variance at the receiver of 20 and the other one is 100. And on the x-axis, we have the number of iterations for federated learning, and on the y-axis, the test accuracy, usually on the MNIST data set. In the case, this is the black line is absolute reference, where which is the case in which the channel is known perfectly and can be inverted perfectly. And the gray line is the one achieved when the number of antenna elements is 2m squared, where m is, again, the number of devices or workers that are present in the fed learning setup. The other lines here refer to essentially less antenna elements. So the higher is the antenna elements, the best is the performance in the case of blind learning and massive multiple input, multiple output networks. Now, instead, we move to another interesting case of MIMO systems, the one with cell-free MIMO. This is investigated in the paper 8.2, in which federated learning in a cell-free massive MIMO framework with channel state information estimation using analog over-the-air function computation with pilot transmissions. In cell-free massive multiple input, multiple output systems, the idea is to perform channel state information in a special manner with the aid of many distributed antennas. And in particular, in cell-free massive multiple input, multiple output systems, we have a large number of access points that are collaboratively serving the same time frequency resources, because they are very well connected with backhaul networks and extremely well synchronized. And the idea is that the various devices that are around the base stations, they send their models to the nearest base station, and then the nearest base station can send this model over this backhaul dedicated link at this central unit, where then the function computation is performed for performing the distributed federated learning. And this is particularly useful, the concept of MIMO systems with the self-free, in particular MIMO system, because as we remember from one of the very first slides on these sections, when the channel is poor for one worker, for one of the wireless devices, then this has negative effects. This introduces a distortion in the computation of and in the estimation of the sum of the modules that is needed in federated learning, I mean the sum of the models. And instead, since here in massive MIMO, self-free massive MIMO, the terminals and the wireless devices, they are close to the base stations, then hopefully this will result in a better channel, and so this negative effect of doing inversions of poor channels will be much less frequent. That's why it's interesting to investigate the self-free massive MIMO and federated learning. And one of the very first papers that does such investigation is this paper 82 by Wu and others. It's called the self-free massive MIMO system for wireless federated learning. Here, the concept is that the main technical difficulty is that at the base stations, there is a number of terminals around these base stations, and they will need to perform some channel estimation. The novelty is that such estimation of the channel is done using non-orthogonal transmissions. So there is no dedicated signaling that is performed to try to extract the channel state information, but instead all the terminals, all the workers around one of the self-free base stations here, they all together they will perform an estimation at the same time and on the same frequencies. Because these devices, they transmit their pilot simultaneously on the same bandwidth. The key idea is that the channel state information is estimated using multiple measurements that are received by so many different access points. So exploiting this self-free concept, the channel state information can still be recovered and it can be used to do the channel inversion. Then the over-the-air function computation, it's happening at each of these individual base stations. The base stations, therefore, they perform a local sum of the local models associated to their connected workers. And then once this local model is, they are summed, they are transmitted using the powerful and dedicated backhaul uplink transmissions. And here there is some results of this study that is again from 2019, so it's relatively recent, and it shows here what is the on this axis we have the I believe the time to perform this the federated learning, at the time that it takes until convergence for the federated learning as a function of the number of access points. And in this graph, we have two kinds of different cells, one with a radius 1 kilometer and one a radius of half a kilometer. And the blue line refers to massive MIMO, while all the users and I mean all the workers, they are collocated in the same cell. And instead the red line is the one that is most interesting to us for what we are studying now, is the self-free massive MIMO. And we can see that there is always a quite good gain, both for large cell and actually especially for large cell, there is a very good gain in terms of the convergence time for federated learning with over-the-air function computation. And this gain becomes smaller when the cell radius also become smaller. And obviously the reason is that the bigger is the cell radius, and the higher is the probability that the channel inversion is not working. So that's why in collocated massive MIMO system with larger cell radius, we experience more distortion, and it takes more time for the federated learning to converge. Instead, it's smaller. I mean, in the cells that as big is 1 kilometer, and instead where we are using the cell-free massive MIMO with many distributed access points, they will reduce this probability of having approved channels, with a consequently better results in terms of convergent time for the federated learning. And finally, now we move to the problem of beamforming and user selection co-design, again in massive MIMO system, where here the idea is to do an optimal scheduling of the workers, and at the same time the estimation of the sum of the models that is needed at the access point in federated learning. This estimation is improved by the usage of precoders and better encoders compared to SISO system. We can see this in particular on this slide, where in single input, single output system, the channel inversion is the only thing that we can do by selecting the appropriate level of power. And then, as we have seen also in the previous case, if the channel is too bad, then we have to set a threshold so that we have to exclude the devices that experience such a bad channel. We could do, I mean, this exclusion, as we commented also in a previous section. In the case of multiple input, multiple output, here we have the advantage that we can do a precoding with a choice of BK, and since we have a matrix of the channel, and then we can do a combining, which is a vector here of a complex element, and this, remember, this precoding also is a vector with complex elements, so we increase the degree of freedom, which could give us a better estimation of this sum to be as equal as possible to the sum of real models that we need in federated learning. And in particular, in this paper 83, Federated Learning via over-the-air computation from 2018 of Young and others, the main concept is that they pose an optimization problem with this kind of signal model, where there is also the user selection. So in other words, the K indexes here are also selected in such a way that the estimation error of the sum of the models of federated learning at the parameter server, at the access point, such estimation as the minimum estimation error. And in this figure, there is just an illustrative example in which on the x-axis we have the time for convergence of federated learning. On the y-axis we have the loss function, which is the smaller the better. And this is there is a benchmark model which corresponds to the case where there is perfect channel state information, and the channel can be perfectly inverted, even though there should be a maximum transmit power, which is ideally ignored. And instead, the method proposed in this paper with appropriate here precoding and combining and the user selection allows to reach such ideal case. These are other variations of less importance here to convey the main message, which again, the main message is that in MIMO systems, we have an increased degree of freedom in choosing the precoders, the combiners, and the users to do a better estimation of the sum of the models that we need in federated learning. And this concludes the part of computation over multiple access channel for machine learning.
Hi everyone, I'm Victoria Fodor. I'm from KTH. I'm professor in the area of communication networks, and I will talk about the next section in our tutorial about orthogonal machine learning driven communications. First, we will address why this is a question that we have to talk about. Then we will review importance aware schemes, and then radio resource management solutions with different objectives. So let's see first why machine learning is a new scenario for orthogonal communication compared to traditional applications like data transmission or video streaming. So we will discuss what are the resources that are involved and therefore has to be allocated, and what are the performance metrics. So let's see, right? This is our scenario with several devices with the local data sets, and these devices together would like to learn a model. In this tutorial, we consider centralized learning or federated learning. So of course, in such scenario, communication resources are involved, as in all traditional wireless networks, transmission bandwidth or transmission time slots, transmission power, and we may also want to talk about retransmissions. Then we have the computational resources, right? We have computational resources at the devices. These are usually limited. And we have also computing power at the central server. We know problem formulations with computing power from recent edge computing literature. But we have a third set of resources that are closely related to the learning task itself, right? And this is the set of participating devices and the data batch size that is utilized for learning. When we talk about federated learning, then we also need to decide how do we utilize the time, right? In federated learning, learning is taking place in iterations. There is a local learning process, then local model parameters are transmitted to the parameter server. The parameter server in turn gives the updated global parameters to the users, and the users start a new local iteration. Right? The time of this local iteration will be called as time of a round. So we also need to decide how long these rounds should be so that we can perform sufficiently many rounds, but still within each round we achieve a good learning performance. So these are the resources involved. What are the objectives? Right? In traditional applications, we usually consider throughput or we consider video quality. When we talk about learning, then we talk about accuracy or learning loss. We may want to maximize the speed of convergence to achieve a high level of accuracy. And at the same time, we may have traditional objectives, like we would like to minimize the resource consumption. We may also want to address fairness, but in this case, fairness among the users doesn't mean fairness in terms of throughput, but data representation or model fairness. Now, unfortunately, the performance of learning in terms of accuracy and convergence speed is usually hard to capture, partially because it depends on the actual data used for learning. So that's why many of the problem formulations that we will see are using proxy metrics. So let's see a couple of such proxy metrics. One can be the sample importance, and here we can see a nice figure from the work from Liu and others. which shows that, well, samples close to the decision boundary are important samples for us. And for example, it also means that, well, it's not just that they are very useful for the learning process, but also that they have to be received with good quality so that they don't deteriorate the learning process. Other possible proxymetrics are participation maximization. Right, intuitively, we might think that the more user participates in learning, the better the learning performance will be. Or instead of optimizing the entire learning process, we might want at least minimize the single round loss or maximize the single round loss decay. And then, of course, we might want to look at combined metrics that consider both learning specific metrics and other metrics, for example, energy consumption. Yeah, so we see that we have both new types of resources to utilize and also new types of objectives and metrics. So of course we need new solutions to manage the resources. Okay, so we will address here two main areas. First, I will talk about important area schemes, and then solutions where radio management, radio resource management plays a key role for various objectives and under various constraints. Okay, so we will follow the set of papers that you can find in our overview paper on wireless for machine learning. And well, first we look at a couple of publications on importance-aware communications, and specifically we will consider centralized learning here. Okay, so first we look at the issue of retransmissions. Retransmission is used in our networks today, and usually the objective with retransmission is to ensure error-free data at the receiver. Now, for learning, we do not need error-free data, right? Some error may not deteriorate the learning process at all. So that's why it is an important question to ask, how much retransmissions actually help the learning process. So for that, we can look at this simplified figure. So the trade-offs are more or less like this. We look at what happens as the number of retransmissions increase, right? So if we increase the number of retransmissions, then the quality of the data will increase. The amount of data that can be then used is decreasing. In this case, we are talking about centralized learning, so it's the quality of or the amount of data that is stored at the users and transmitted to the central server. So as a result, well, accuracy depends on both. So we get an accuracy curve that has a maximum, and with that we have an optimal number of retransmissions. Now, what Leo and others concentrated on in this paper is that, well, the number of retransmissions should depend actually on the importance of the data, right? Again, if a sample is far from a decision boundary, then it's not a big problem if actually it's received with noise. If the sample is close to the decision boundary, then it's important that the noise is small so that it doesn't deteriorate the process of learning. So here they suggest a metric to control the number of retransmissions. They suggest to have a sample-dependent limit for the required signal-to-noise ratio, which depends on this U, which is the utility or the importance of a sample, which is now here expressed as a function of the distance to the decision boundary. Okay, as a result, we can decrease the number of retransmissions significantly. So here we see a figure on the number of retransmissions as a function of the distance to the decision boundary. And we see that the proposed solution decreases the number of retransmissions significantly compared to a solution which is only aware of some kind of predefined SNR threshold. Other solutions that consider importance are solutions that concentrate on the selection of the user who should share its data or transmit its data to the central server. So the same group followed the previous work and then continued to use the importance metrics of the closeness to the decision boundary, but now to select the device to transmit. Here, the proposal is to combine the metric of importance with a metric on the channel quality. Right, so this is their suggestion. We should select the user K to share its data if this data is important enough. So this is this utility value, but the channel quality is not too bad. So we can see the result here. Here we have the achieved test accuracy as a function of the transmitter power levels. The proposed scheme is shown with blue, while we have other schemes here to compare with that are only considered importance or only consider the channel quality. And while we see that there is a significant gain for nearly all transmit power values. So this is about data importance, and we will get back to this towards the end of this presentation. But next, we consider radio resource management, and actually from this point on, we will consider or focus on federated learning. Okay, so again, this is our scenario. We have several devices with their own local data set and their own learning model as well. Right, these devices update their local model and then transmit model parameters to the parameter server and receive model parameters, global parameters from the parameter server. So what are the challenges in this scenario? Well, local learning can be time consuming at the devices, and it can also consume too much energy for this usually battery driven devices. Also, this model parameters has to be uploaded to the parameter server, and well, these can be quite large vectors in many learning problems. So yeah, in addition, we have the problem that it's very hard to capture the performance of the entire learning process at the beginning of this process. So we will look at different approaches. We will look at participation maximization. We will discuss single round learning rate maximization, and also suggestions to actually minimize the total learning time for given required activity. Yes, so first we look at papers who aim at maximizing the number of participating users. And we look at the proposal from Nishio and others. Right? The goal is to schedule as many users as possible in each round when we assume that the time available for these local iterations is predefined. Okay, and then the idea is to optimize this time via experiment. In this work, greedy selection of users is suggested. right? The delay of an iteration round consists of computation at the local user, uploading of the samples, computation locally, uploading of the samples, aggregation at the parameter server, and also sharing this data with or sharing the updated vector with the devices. So in this paper, the idea is to add users to the set of users one by one in a way that every time this T round is increased as little as possible, right? And we do this until finally we reach the limit. So let's see how this solution performs. On this figure, we see how the accuracy increases as the time increases as well. We compare this greedy solution to a solution where users are selected randomly, and this is what is shown by a green curve. Right, all the other curves show our optimized scheme, but for different lengths of T round. Right, what we can see here is that that the length of T round affects significantly the convergence speed. So indeed, the value of T round has to be part of the optimization problem. We also see that the achieved accuracy, for example, in this example is not too high, and this is because this example is about non-IID data distribution. So we can recognize here that it is also important to consider data representation fairness for user selection. Okay, so the previous paper didn't consider the actual energy used for the communication. So the next step by Zhang et al. Is to keep track of the consumed energy while also trying to maximize the number of users participating in an iteration. They do this by defining a combined objective function, which includes the transmission energy, but also the number of users participating. Right. So with this second term, we are trying to maximize the number of participating devices, but at the same time, the consumed energy shouldn't increase too much. This paper also addresses then the optimal allocation of the bandwidth. So what can we see how this solution performs? We look at the performance of this proposed scheme as a function of the time limit, so the time of a computation round, the learning round. We look at the learning accuracy we achieve and the energy consumption ratio or energy reduction ratio compared to a baseline scheme. This is our baseline scheme where the bandwidth allocation is not optimized. Right. What we see here is that if we have a reasonably long communication round, that is many users can participate, then the proposed scheme achieves high accuracy, and there is still a very high energy reduction rate, so up to 70%. When we have very little time for a round and very few users are selected in the proposed scheme, and that's why the accuracy is very low. But at the same time, we have huge energy savings. Of course, with this parameter lambda that we have here in this objective function, we can balance this trade-off between participation, accuracy, and energy consumption. Okay, so up till now, we were talking about participation maximization under different constraints. Now, we will look at papers that aim at minimizing the single round learning loss. Okay, still at the beginning, considering a fixed time for a round. Okay, so let's look at the first paper from Yang et al. Again, we have the bunch of devices, and here an important part of the problem formulation is that these devices are very heterogeneous in terms of computing power, in terms of available energy, in terms of channel quality to the parameter server. So what this paper suggests is that, well, then these devices have to use time in a smart way, and it can mean that not all the devices have time to do the same number of local iterations, right? So they suggest to optimize the number of local iterations, and with that, the time spent with local computation, right? This is the green part in this figure, based on the capabilities of the devices. Right, the goal is that if we consider all the computations at the devices and then the time they need to actually transmit their model updates to the parameter server, then each of the users should finish more or less at the same time. Right, so this is the optimization that is performed, and for that the authors utilize analytic expressions on the trade-off between the learning loss and the number of local iterations. So let's see how important it is to optimize the number of local iterations. Again, we have here the time available for one round, and here we have the total energy used. So again, this blue line is energy consumption of the proposed scheme, and we can compare it to other schemes that only optimize some aspects, right? So, for example, the line with yellow considers only optimal bandwidth allocation, while the red line considers achieved accuracy. The purple line is a randomized scheme with random bandwidth allocation. So again, these results show that that actually both the wireless environment and the learning path should be considered when we optimize the resource allocation. Okay, so another problem formulation, still with the objective of minimizing the single iteration learning loss, is to consider scenarios when packet loss is possible. Right, in the papers that we discussed up till now, usually a coding scheme is assumed so that we can reach the Shannon capacity. In this paper, instead, we consider that the system or the wireless connections can be in outage and packets can be lost. So the objective of this paper is to minimize a single iteration learning loss by selecting as many users as possible, but still keeping the packet loss on a low level. The reasoning behind this problem formulation is that once we include many devices into one round, there is less communication resource available for one device, which leads to packet losses. So the solution of this optimization problem is then built on theoretic results on the loss probability and learning rate trade-off. And with the help of these theoretic results, the authors optimize the set of users participating. Right, so again, when we would like to evaluate the scheme, we have to look at the accuracy. Right? This is what we have on the y-axis as the learning process goes on. Right, this is the number of iterations. The black line is the one achieved by the proposed scheme. And again, we compare it to schemes that only do a part of this optimization. So, well, we look at a randomized case and a case that selects the users, assuming that there are no constraints on the communication, and another scheme that only considers the wireless environment and doesn't consider the learning process itself. So we see that combined optimization again achieves, in this case, 5–10% accuracy gain. Okay, so with the next paper, actually, we take a significant step because after the objectives of optimizing a single round, the objective of the next paper is to actually minimize the total learning time. So let's see how can we formulate such a problem. Yes, so remember, this is the figure that explains our learning process with different lengths of learning rounds. So if the learning round is long, then the achieved gain of one round is significant, but we don't have much, we do not have time to many of such rounds. So the paper from Xi et al. Addresses this problem and aims at optimizing this time of local iterations. And then within this time, their objective is also to maximize the number of users that can be scheduled. So that in the end, the total convergence time is minimized. So even in this paper, we find a nice theoretic model where the number of global rounds or epochs is expressed as a function of the acceptable learning loss at the end of the learning process and the number of scheduled devices, while the number of scheduled devices affect the time of one learning round. Yeah, so let's see what kind of results we can achieve here. Again, we look at the achieved test accuracy as time goes by, and we can see that the proposed scheme, this one with purple, achieves significant gain compared to solutions that schedule the users with the best channel, schemes that select random users, and also schemes that have a predefined time for one round. Right, in that case, right, these are these green dotted and orange dotted lines. In this case, the actual performance that we get in the end depends very much what is this T round value that we happen to select. So what can we conclude from these results? We can conclude that again, it's important to consider both the learning process and the wireless environment when we select the users, and indeed it is worth to include the time of a T round in the optimization process. Okay, so with this, we read the last two papers that we would like to discuss in this part of the tutorial. And these last two papers consider new parameters for optimizing the learning process. The first one will consider the size of or the amount of data used for the local learning. And finally, the last paper that we will talk about gets back to the idea of data importance. Okay, so let's look at the effect of the batch size of learning. Right, so the objective of Ren and others in this paper is to determine how much data should be used for the local learning process at the devices, such that we have a fast and efficient learning process. So first of all, again, they would like to optimize the entire learning process, so reaching high accuracy within limited time. And they do this by defining an objective as a ratio of the loss decay and the iteration time. Then to use an iteration time the best possible way, they also optimize the amount of data that is used for the local iterations for each user, again, considering the capabilities of the user. They also recognize that while when we consider small amount of data, they don't have significant effect on the local latencies, but after a while, with increased batch size, the computation time increases significantly. So, well, to capture this optimal batch size, they also find analytic results that connect the loss decay and the batch size, right? And then with this, they can optimize the learning and communication parameters to achieve a good loss decay iteration time ratio. So let's see what kind of results we can find here. Here again, we consider test accuracy as a function of the training time. We look at a couple of curves that are close to each other. The red line is the performance of the proposed scheme, while the blue line was the one that happens to consider all data at the device, and the purple one is a line that selects a random batch size. Right, again, we can see again in all regions, and especially at the beginning, so we can see that the proposed scheme achieves faster convergence than simpler solutions. Okay, and finally, as considering the last paper for this section, we get back to importance metrics. So Ren et al. In this paper introduce a solution that is based, that selects the set of users for each communication round based on the importance of their model update. So again, as a theoretic result in this paper, they show that the gradient norm is a good importance metric. And then they define the user selection probabilities for each round as a function of the gradient norm and again the upload time, right? So in this case, again, we have a solution where learning performance in terms of gradient norm and the networking environment in the terms of the upload time is combined. Here we can see the impressive results of this paper. So again, the first figure, we follow the test accuracy as a function of the training time, and with the red, we can see the proposed scheme, that it has a very fast convergence to a high level of accuracy. Right? This is compared to two solutions. In this case, we consider a scheduling solution that considers only the channel quality. Right? We can see that it achieves a high convergence rate at the beginning, but by the final accuracy is rather low. In contrast, if scheduling is based on data importance, then the convergence is lower. It may take long time to actually upload these gradients, but the final accuracy will be good. Again, in this paper, they conclude that the number of devices scheduled in each round has significant effect. In this case, it's not included in the optimization problem, but well, in this second figure, we can see that as the number of scheduled users changes, here this is noted by M, the learning performance differs. Right? We have a couple of extreme cases here. The yellow line shows a scenario where there are many users scheduled, which means that each round actually takes a very long time. And in this case, it leads to low convergence. Well, with this, I completed this section of overviewing recent results on orthogonal machine learning driven communications. And we go on in the tutorial with open challenges. Thank you very much.
Hello again, and welcome to the fifth and final part of this tutorial. Here we're going to discuss some open challenges and future research directions within wireless for machine learning. Personally, I'm going to talk about this first part about over-the-air computation, and then I'm going to leave the floor to José Merton Paros da Silva Jr. to talk about these remaining three parts. Starting off, I'm going to talk about the practical implementation of over-the-air computation. In particular, I'm going to talk about experiments and test beds, and I'm going to talk about large-scale implementation. At the top here of this slide, you can see a proposal for a transceiver chain that's designed for over-the-air computation. It's taken from this paper by Guangxu Xu at the bottom here. Two of these blocks in the transceiver chain are outlined by these dashed lines, and that is because these blocks are not available in a standard chipset that we have today. In other words, if you were to use a proposal such as this one, we would have to have custom hardware at all of the edge devices that want to participate in such a network protocol. And if we're talking about a large-scale implementation, this would of course be very expensive. Replacing the hardware of all of our mobile or IoT devices is a very expensive operation. And for this reason, all current experimental setups use software-defined radio. There's basically not been any company or any research facility that have implemented ASICs for over-the-air computation, and we do not see any commercial implementation so far. Also, the experiments we have right now have been under quite limited network conditions. Generally, it's been indoors with line-of-sight communication, static devices, and a small number of devices. So what can we do about these problems? Well, there's been some ideas on how we can leverage the current chipsets we have to do over-the-air computation. Carlo Fischione talked about one paper on digital over-the-air computation that basically uses BPSK modulation and then takes the power control functionality to emulate an analog modulation. This is a very interesting idea, and if it works well in practice, that could be a big saver in terms of cost of implementing this system. However, so far there's only been one paper on this, and more work is definitely needed. Secondly, there's also been many suggestions to use the timing advance functionality of the current LTE standard to perform the synchronization. According to some calculations, this timing advance should be enough to do over-the-air computation, but no one has experimented with this in practice, so we still need to try it out. And of course, it would be interesting to see some more ambitious testbeds that have more devices, that have more realistic conditions, and maybe some that are outdoors using dynamic channels. Finally, there's never been any papers that combine federated learning and over-the-air computation outside that of a simulation. And of course, the kind of estimation errors we see in a simulator are not going to be the same as we see in practice. And we still don't know how these more realistic estimation errors would combine the federated learning convergence. So there's some room here for experimentation as well. Next, I'm going to talk about imperfect over-the-air computation. And by imperfect, I mean some things that we have removed in the current theory by assuming it away, but that is going to be present in a more practical network. First off, we can talk about channel estimation. As mentioned in the primer, channel inversion is a very important part of over-the-air computation, because without it, we get this weighted sum that is very far from the true sum that we need in our gradient aggregation. However, if the channel estimate is not the same as the channel, which will always be the case, we'll still have a weighted sum here rather than the true sum. We have not yet seen any papers that analyze the impact of this imperfect channel estimation and therefore the imperfect channel inversion on federated learning. So this is a gap that we still need from the literature. Moving on to synchronization, we know that even if devices are just slightly out of sync, that can have a major effect on the over-the-air computation. Now, for the case of pure over-the-air computation without federated learning, there have been some papers proposing more robust over-the-air computation schemes, such as this Mario Goldenbaum paper here at the bottom. They show that you can make over-the-air computation quite robust to small synchronization errors, but there's still, of course, a risk if the synchronization errors get large. But when you combine synchronization errors with federated learning, we don't have any works on this yet. So we still don't know how synchronization errors would impact our classification accuracy or the convergence analysis. Next, I'm going to talk about the design of the estimator. And when I talk about the estimator here, I talk about the estimate of the uplink gradient aggregate. In one way, the power control can be seen as an estimator, because this is going to define what our received function is like. And by designing the power control, we are indirectly designing the estimate of the function that we get at the receiver. Now, as I mentioned in the primer, we have found an optimal power control scheme. However, this was optimal under quite strong conditions. The first one is that we have global CSI knowledge at all devices. So every device knows the CSI of every other device. That we have single antenna devices and a single antenna server, and that the sensor signals are assumed to be normally distributed and IID. So this is a good first step. We have the optimal power control, and that was found in this paper by Xiao and Chow here at the bottom. However, it still leaves many open problems. One is that in MIMO, we don't know the global optimal solution. We have some good heuristics, but we don't know the best way to do it yet. We also don't know what happens when we have partial CSI knowledge. Maybe it's unrealistic to assume that we can get global CSI knowledge in practice, and then what should the power control look like? This is a completely open problem. The third problem here is a little bit more subtle, but it has to do with this assumption on the sensor signals. Now, in this power control paper, the one mentioned down here, they made the assumption that all of the sensor signals were stochastic, including the sensor signal of the device itself. So the device that is going to transmit doesn't know the value of its own sensor signal. Of course, in practice, you do know this, so there is some additional information that could be used to make the power control stronger. But it also makes the problem harder, so no one has solved this problem yet. Finally, there is some work to do with combining power control with federated learning. Up here, and in most other power control schemes, we have simply been minimizing the mean squared error, but that might not be the right metric for the case of federated learning. For instance, we could consider maximizing the convergence rate given a certain power control scheme. There are also other interesting directions besides power control. One recent work have been talking about using Bayesian estimators when we're doing the uplink gradient update. In this paper down here by Fan et al., we are using the sparsity of the gradient as a prior on the estimate. So if you look at this figure, they have plotted the gradient vector here. So in the x-axis, we have the elements of the gradient vector, and in the y-axis, we have the time or the communication runs. We can very clearly see that there's some strong temporal correlations in time over the sparsity of these gradients. So what we can do with this is that we can train for a couple of rounds, and then we have some information about what the gradient should look like and use that as a Bayesian prior in our estimation. There's also some potential for ideas coming here from estimation theory. We still have not had anyone talk about what the minimum variance unbiased estimator is, and there's still been no discussion about the bias variance trade-off. Potentially, there is a point here that is better than minimizing the mean squared error. That all depends on what kind of gradient is most useful for the federated learning problem. Finally, we could also consider an estimator that doesn't care about the mean squared error, but instead tries to maximize the probability that our gradient is in a descent direction. If we have very heavy noise, then we will see that sometimes the gradient goes in the wrong way, and we're actually diverging from the true solution. So perhaps it would be better to then use an estimator that maximizes this probability. Finally, I'm going to talk a little bit about something I call the communication estimation trade-off. And what I mean by this is something related to digital communication systems. So in a digital communication system, we always have a coding rate that we can use to improve the likelihood to make our bit perfect reconstruction at the server. And if we select a higher rate, then that means that we're increasing the communication efficiency, but we're reducing the estimation in that sense then. However, in analog communications, we don't have these codes. So how are we going to make this trade-off? So basically the topic here is to sacrifice communication resources to improve the estimation. One suggestion to do this is simply to just do some retransmissions in this uplink aggregation step. In one recent work on this, we can see that by increasing the number of retransmissions in the uplink step and then taking the average of these transmissions, we can significantly reduce the estimation error. Here we have a single transmission, here we have 2 transmissions, 4, and then 8. And if we combine this with federated learning, we can see that even under very noisy scenarios, such as this one, if we have a single transmission, the noise might be too much to really get a good convergence for the federated learning algorithm. But as we introduce more retransmissions, we can get to some stable point and we can get a much cleaner convergence here. Also notice in this graph that when we're using 4 transmissions instead of 1 transmission, we're considering that you have to stop the training 4 times sooner. But even if you stop 4 times sooner, you're still able to reach a much higher level of accuracy. Also, in the primer for over-the-air computation, I mentioned that there are no forward error correcting codes for over-the-air computation. However, considering that we now have some proposals for digital over-the-air computation schemes, maybe there is a possibility to do something. So far, we've not seen any channel code that would be compatible, but maybe one is out there. Another interesting question is when you should choose to do over-the-air computation and when you should choose to do orthogonal transmission. At some point, if the network conditions are sufficiently bad, as we can see in this graph on the right, the estimation error is simply unacceptable. The model will have such a low accuracy that it's not worth the gain that we're getting in communication resources. So there has to be some threshold where we would want to choose either over-the-air computation or orthogonal communication. So far, there has not been any analysis on how you should make this choice. Another thing to consider for this choice is when we have very fast fading. Since over-the-air computation is reliant upon this channel inversion, it's important that the channel stays quite stable throughout the transmission. If the channel changes very fast, the estimation error is going to grow very quickly. Now, there has been 1 or 2 works on over-the-air computation that works in very dynamic channels, but this work is still very young and there's more to do. That concludes my part of the open challenges and future research directions, and I leave the floor to Merton.
Hello again. We discuss now the section on scheduling and resource management within the open challenges and future research directions. So here we divide this section, this subsection, into data importance metrics and staleness and energy efficiency. Let's first go through the first point, data importance metrics and staleness. So as we know, in cellular communication, the device selection that we have seen before in federated learning, for instance, this device selection acts as the scheduler, and this scheduling is done by the parameter server, which in cellular communications is the base station. So then we have now the question, how can we select the devices that will participate in this training? Should we select the devices that have better channel conditions, or should we select the devices that have more important data? So here we have a need for new scheduling mechanisms that consider both channel conditions and the data importance. We have seen some of these metrics before in the previous section 4 with Professor Vittorio Fodor, but more investigation is necessary, specifically to establish the convergence of many of these device selections when considered in the training. And also we need to take into account the local computability on resource-constrained devices, because here we may select devices that are also more capable of doing the training. Another important aspect is that the device selection can be done per communication round or not. So we may select the devices every 10 global rounds, let's say. So this is another option that we can decide and that we can consider when designing this scheduling. But once this scheduling metric is decided, we need to now understand and to check when do we update this metric. So now the data importance and the channel conditions, they need to be fresh, they need to be recent, they need to be new. So here the device with important data is no longer important because a lot of time has passed and this information is no longer important. Or the channel condition of the device is not good now because it's going through some deep fade. So in this situation, the data staleness needs to be further investigated, including the convergence of these methods and the frequency of update of this scheduling metric. So recently, we have seen only one work using a common technique that takes into account this age of the information here, together with federated learning. And this paper is mentioned here below. So we see this, that more analysis is necessary in this field here of data importance metrics and also considering the staleness of this scheduling. So now we go through the energy efficiency aspect of the scheduling and the resource management. So as we know, the local training consumes a lot of energy from the devices. And these devices we have many different impacting parameters. For instance, the local number of iterations, the number of global communication rounds, and the transmit power that these devices are using. So all of these are factors that are impacting the energy consumption of these devices. And some works, they have optimized the energy consumption in a joint communication and learning problem. We have seen that in the previous section 4. So for instance, they have considered the minimization of the energy consumption while fulfilling some learning constraints. We have also seen works using the maximization of the learning accuracy while fulfilling some energy consumption constraints. So the question that we ask now is, can this local training happen without depleting the battery of the devices? So this is a question that has not been proposed in the recent literature. It's a very new question. And this leads to this following situation or this following question. So is it possible to harvest sufficient energy to support the training that we do in a distributed manner? And here we have this figure in which the devices here, they are doing, for instance, federated learning. They are using here the local model, transmitting to the parameter server and receiving from the parameter server the global update. But together with the global update, they also receive energy. So they're harvesting energy to support the energy that they spent in the computation locally and in the transmission to the parameter server. So this is a very new idea, and so far only 2 works have analyzed energy harvesting supporting this distributed training. These 2 works are here mentioned, and as we can see, they are from this year, so very recent works, which means that a lot of unknown in this area is still up there. So we should really consider working on this energy harvesting, supporting distributed training. So now we have other challenges which are scenario specific. The first one is on vehicular networks. So here we have an example. We can see here some cars, some trucks, and some motorcycles, and they are using, let's say, federated learning here. They're gathering some data and they're doing some distributed training. And in autonomous driving and advanced driver assistance systems, so ADAS, they have severe communication challenges. So we need to fulfill low latency or ultra low latency. We need to have a very high reliability. We need also high data rates. And on top of this, we also have a fast varying communication channel. So recently, the current literature uses federated learning for vehicle networks, but they're not using vehicle networks for federated learning. And specifically on this aspect here, over-the-air fulfills some of these challenges, but it is still very complicated to use over-the-air because of the dynamics of the channel. So only 2 works on the over-the-air community have considered the channel dynamics here. And we are mentioning them here. And one specifically is on edge learning. So with this, we see that a joint communication and learning goal towards this accurate prediction needs to consider the following: a high privacy requirements, because these vehicles cannot exchange the information openly. We need decision-making to be extremely fast. And also we have very high different goals. And these goals, they have different requirements. So we can have traffic detection, motion prediction, and trajectory planning. And depending on the goal here that you have, the requirements may also be very different. So the question here is, how can the system ensure a reliable prediction and decision-making for ADAS and autonomous driving? So this area is very open now. There are basically just very few works on this, and a lot of investigation is needed here. The next one is the Internet of Things. So it's a bit more general. As we have seen this slide with Professor Carlo Fischione, we have that each IoT scenario, so massive IoT broadband IoT or critical IoT or even industrial automation IoT, they have very different learning methods and they have very different communication constraints. So here, broadband IoT, we have very high throughput, low latency, and large data volumes to be exchanged. But then here in critical IoT, we need to have ultra reliability, ultra low latency, and very high availability. So very different communication constraints. And for each of these scenarios, we have specific ideas and challenges, both from the communication and from the learning. So for the massive IoT, the device scheduling is one of the challenges, also together with the limited bandwidth. And notice that here, the devices, they are highly heterogeneous because we can have a very good sensor together with very cheap sensors. And we need to consider these two together in the learning and in the communication model. Then in the broadband IoT, we need to support high data rates with low latency. And together with this, we also need to exchange large volumes of data. So here, we need to also consider a specialized joint communication and learning for these scenarios. Then for critical IoT, the prediction and the decision-making must happen extremely fast in the 1 millisecond or lower time scale. So not only the communication needs to be fast, but also the prediction needs to be fast. Finally, in the industrial automation IoT, we need to ensure that the privacy is guaranteed and that we have very low privacy loss, while we also have very high security. So for all of these 4 scenarios, they have very limited works here. We have many works which are general on cellular communication, but no works which are specifically targeted towards massive IoT, mean very few works, or to broadband IoT, and especially to critical IoT and industrial automation. So we need more works which are targeted towards these specific scenarios. So finally here, we have the security and privacy in the open challenges and future research directions. Here on the privacy, first one that we have here is that remember that it is impossible to see who is transmitting the model updates in COMAC. But is this a blessing or a curse? Because it's easy for an adversary to send malicious model updates to harm the training. And no one can know who is sending this information, because in COMAC, we lose that. And this is an example of model poisoning, which is represented here in this figure. We have here a figure, which is a panda. We have some confidence that it's a panda. And then the adversary is introducing noise here, a very specialized crafted noise target towards this specific sample. And then the classifier will change completely here. Now we are classifying this as a gibbon instead of a panda. So all of this is to say that this type of poisoning can happen in COMAC. And remember that anomaly detection via the individual models, it's not possible. So this tells us that extensive analysis is necessary on this specific scenario. And here we have one specific work that is considering that. And here it uses a sequence of spread spectrum codes. So right after the analog amplitude modulation, we include some blocks here in which we consider this ESS code, and we use a pseudo noise sequence generator. And then the idea of using these codes is to legitimate the users that have the common code. So the users without this common code, they are suppressed. So that's a way of also identifying the users that you want to participate, that you want to aggregate. But notice that here, this is just one work. There are not any other works. So here, more information is, or more investigation is necessary. And finally here, we have also another example. So here we have the classical eavesdropping problem. We have Alice that wants to communicate with Bob. So here we have a device communicating with the parameter server, and then we have the eavesdropper here, Eve. And then in orthogonal transmissions, we can use physical layer security to help mitigate these adversarial attacks. So with this, we can avoid this eavesdropper or the attackers using some coding or transmit power or transmit precoding schemes. So then here the question is, how can the system design the joint communication and learning mechanisms to avoid such eavesdropping? So how can the system design together the coding and precoding together with other learning parameters to mitigate this situation? This is also an open problem, and there, to the best of our knowledge, there have been no works on this. So this is also very interesting to analyze. So with that, we have concluded this tutorial here, the 5th section. And if you want more detailed information about any of these sections, you can also check our paper on our site, Wireless for Machine Learning. And I suggest you to do that if you're more interested into some of the other references that we point for each specific scenario. And with that, I'd like to conclude the tutorial on wireless for machine learning. Thank you very much.